Yes, refraction, total internal reflection, and apparent depth, all these concepts. Just hold on. Let me just turn on my chats properly. I'm not able to see it. Just 1 second, guys. Okay. Am I audible, guys? Am I visible? Do let me know. Is everything seen? Okay, I think it is. Okay, so today in the ray optics number 2 lecture, we are going to do prisms, we are going to do lenses, combinations, silvering, and also optical instruments, all in this lecture. Okay. So let's begin with the next part, ray optics part 2. Ready for this, my dear lions? Do let me know quickly. Am I audible, visible? Put up a thumbs up, say hello, hi. Yes, all right, Geeta. All right, Adiksha. Perfect. Perfect. No voice, is it? Check. Is the voice perfect? I'm not sure. Yep. Is everything fine? Let me know, guys, quickly. Then I'll begin with the class. Okay. Okay. Perfect. Chalo. So let's begin. Let's begin. Let's begin. Now audible. Okay. So let me tell you, my dear students, if you recollect, we have done refraction properly. We have done total internal reflection also properly. All these things we have done in the previous lecture. So let's start with prisms now. Now, when I use the word prism, a lot of people generally start thinking of basically this, where some white light is entering and you are seeing these rainbow colors. That is, yes, a prism, definitely. But in general, what is a prism kind of a problem? So let me explain that to you with a simple explanation, and then we will see all the terminologies associated with a prism. See, imagine if I take a glass slab. If I take a glass slab, so this is nothing but a glass, this is nothing but a glass slab. And if you pass a ray of light, if you pass a ray of light through that particular glass slab, what happens? It first refracts and then again refracts on the other face and it comes out like this. And if you observe carefully, the original ray was going in this particular direction. It deviated and finally came out. And eventually what you notice is the final ray has shifted laterally. There is lateral shift. There is lateral shift, and we have seen the formula for the lateral shift, but the deviation is zero. That means the incident ray and the final ray, both of them are parallel to each other. This ray and this ray, they are just parallel to each other. That's why there is no deviation. Do you remember this? Correct, everyone? Now just imagine, okay, just imagine the two faces of the glass slab. Just imagine the two faces of the glass slab, they are not parallel anymore. Rather, they are making some angle. Let's say the first slab face is here, the other face is somewhere over here. Now, when you draw the same incident ray, let's say it is falling like this, okay, it refracts at this particular point like this. And when again it refracts, there is a good chance it might not just come parallelly. It might not just come parallelly, guys. So we'll probably go something like this over here, maybe, example. And you will see that our original ray was going like this. Our final ray is going in some other direction only. It is going in some other direction only. So right now, there is definitely some deviation. There is definitely some deviation, and this deviation is not zero. So when the faces of a slab are basically parallel, then there is no net deviation except for a shift in the ray laterally. But when the faces of a slab, they are making certain angle, they are non-parallel, the final ray is making some angle with the incident ray. The final ray is making the emergent ray is making some angle with the incident ray. This is exactly the concept of a prism. Prism is nothing but a glass slab with non-parallel sides. So if I just extend this further over here, this particular angle that you see over here, this A, this is called as the angle of a prism. This is just called as the angle of the prism, and there is some deviation which is produced. So this is a slab with non-parallel faces. Non-parallel faces. Such a thing is basically called as a prism. Such a thing is called as a prism. This ray which is falling onto it is definitely called as our incident ray. This ray is obviously called as our emergent ray. This is our emergent ray. Are these definitions absolutely clear? Are these definitions absolutely clear? So that means which all will be prisms? This is a prism. Even this is a prism. Even this is a prism. Even this is a prism. As long as you have two non-parallel faces, something like this. Two non-parallel faces. Two non-parallel faces, incident ray and emergent ray. All these are prisms. All are prisms. All are basically nothing but prisms. Keep that in mind. So there are a lot of geometrical aspects, geometrical formulas related to the prisms. We'll start seeing all of these one by one. So let's start with a prism first and see all the important angles in it, and all sorts of things. So this is some random prism. Remember, the base does not really matter. First of all, this I have already mentioned. This is angle of the prism. Then let's start showing the incident ray and all those things. So this is, let's say, the incident ray. Then it refracts, and again it refracts over here. So we also need to show some normal at these places. So this is normal, and this is normal maybe over here. Okay, perfect. Let's start marking the angles now. Let's start marking the angles. This angle over here, I will call it I1. This angle over here, I will call it R1. This emergent angle, the angle with which the final ray comes out, I will call it I2. Why I2 and why I1? Because reversibility principle of light. If I send the light from here, this becomes emergent. If I send the light from here, this becomes emergent, and this becomes incident. So they can be interchanged depending on the direction of the ray. So I am using the same symbol. I'm just calling 1 and 2 depending on face number 1, face number 2. So this will be the incident if the ray comes from here. This will be the incident if the ray enters from here. So the arrow mark has no significance because of the reversibility principle of light. As simple as that. And again, this will be the internal angle of R2. That's all. So these are some of the important angles which we will be generally marking in case of a prism. Now, I all want you to focus on certain points. Let's say I call this point as P. Let's say I call this point as Q. Let's say I call this point as R. Okay, now everybody focus your attention on the triangle, PQR. In the triangle PQR, the sum of the angles should be 180 degree. So angle P plus angle Q plus the angle R should be 180 degrees. Now what is angle P? Angle P is basically angle A, whatever, A degree, 60 degree, 30 degree, 45 degree, whatever it is, right? As simple as that. Okay. Next, Raghu Kirtigan Velumurugan. How do I know, Bacha? We have Namrata ma'am over here on the channel. Okay, Shivan sir has moved out of the channel to the Master Tamil. Okay, so there are two separate channels. So this is the channel in English where Namrata ma'am is teaching you mathematics. I think you have probably visited the channel after 2 years or something. So it's been a long time. All right. What about angle Q? Angle Q, if you notice, this whole thing is 90. This is R. This is R. So this small angle over here, this particular angle will be nothing but 90 minus R1. Same thing with this over here. This will be 90 minus R2. So hence, those internal angles, I can just call it as 90 minus R1, and that is nothing but 90 minus R2. That is nothing but 180 degrees. So rearranging it further, A minus R1 minus R2. Take that 90 and 90 on the other side, it will become 180 minus 90 minus basically 90. What is 90 plus 90? 180. So that will just become 0. So therefore, A will become just R1 plus R2. This is a very, very important formula. Angle of prism is this sum of the internal angles of refraction, R1 plus R2. As simple as that. I hope this is absolutely clear. Yep. Thank you, yours truly, Akshay. Yep. I'll wear it after some time. Not now. Okay. That was the first formula which we saw. Then you have other formulas too. Like we can apply Snell's law. So apply Snell's law. Apply Snell's law on both faces. On both the faces. Obviously, Snell's law is valid always, so we can still use it. So if you assume the material of the prism is mu, and outside material assume it is to be air, then we can just simply write. For this part, sine of I1 divided by sine of R1 is basically the refractive index. And if you look at it from the other side, then sine of I2 divided by sine of R2 is the refractive index. So this is just applying Snell's law in case in a problem we need to find something. For example, refractive index is given to me. Example, I know the incident angle. Because I know the I and because I know mu, from these two I can find R1. Once I know R1, I can find R2 using this relation. Because R1 plus R2 is A. If I know R1 and the angle of prism, I will find R2. Once I find R2, and because I know mu, I can find I2. So I'll be able to find this angle. So this is how you will be able to solve some questions where mu, I, etc. is given to you. As simple as that, right? So these are basically geometrical formulas, nothing more, nothing less. Keep that in mind. Okay. Next important relationship which you should know again. See, let me just create a duplicate for this. Okay. See, our original ray which is there, incident ray, it was going like this. It was basically going like this. Our final emergent ray ended up going like this. So clearly there is some kind of a deviation which has occurred. There is clearly some deviation which has occurred, delta, and I want to find how much the deviation is. Now, here is how I think about it. This deviation has occurred because of two instances at two different phases. Once the light deviated slightly here on this particular phase, it has slightly bent, and second time it bent again over here. Maybe it bent by 10 degrees here it bent by 15 degrees. So 10 degrees it has turned, then again it has turned 15 degrees. So totally it has turned 25 degrees. So if I add the deviations at both the faces, I will get the total deviation. Yep, I hope this is very, very clear. So hence, delta will be nothing but delta 1 plus delta 2. Delta 1, delta 2 are the deviations on the respective faces. For any kind of refraction, recollect what is the deviation formula. In case you have forgotten, let me also remind you about that. If this is our face and this is our normal, and our ray comes in like this and deviates like this, right? So this was our original direction. So this would be our deviation. How much will that be? Well, this was I. If that is I, obviously this is also I. If this is I, obviously this is also going to be I. And how much is this? That is R. So how much is delta? Delta is nothing but I minus R. Delta is nothing but the bigger angle minus smaller angle. Assuming I is more than R, if R is more than I, then it will be R minus I. So that's why we put modulus. So that's how you measure the deviation. So hence, What is delta 1 and delta 2? Well, delta 1 will be nothing but I1 minus R1. I1 minus R1, in this case I1 is more than R1, so I'll just leave it as it is. And how much is delta 2? It is I2 minus R2. Perfect. So let me bring I1 and I2 together. So I1 plus I2 minus, here I will have R1 plus R2. Oh, but wait a minute, this looks something very familiar to me. R1 plus R2, I just told it to you right over here. R1 plus R2 is nothing but A, which is angle of prism. So instead of R1 plus R2, I just put it as A. This will become delta. This becomes our next important formula. This becomes our next important formula. Is that absolutely clear? Such an interesting derivation, such a straightforward derivation. Yep. So, Madhul, how to get the Jungle Book and DPP, etc. Yeah. Okay, so you will just get it over here. Just get it over here. As you are watching this class, in the description box, you will get it. Where is it? Where are we? Ray optics, right? Just go to ray optics. Just go to the description box. Just go to the description box. Where is it? The description box is right over here. Yep. Click here to join the Jungle Book. Just open this. That's it. It will open this particular page. Click on this. It might ask you to register. Just create a free account. Okay, that's it. You have to just create a free account. You will see all the chapter names, physics, chemistry, maths lectures are arranged separately with the dates, with the notes handwritten, with the DPP. All the DPPs are right over here. As soon as the lecture is over, within 1 or 2 days, we upload the DPP as well. Is that okay? Perfect. Now let's proceed ahead. Let's proceed ahead. Some books, yes, they will use I plus E minus A. Here we are using I1, I2 and all that. Okay, so it's one and the same thing. Don't worry. Okay, perfect, perfect. Now that we have learned about all of this, just 1 second. We have learned about all these particular second. Delete this. All these angles. There is a very important graph of angle of incidence versus angle of deviation. Just like, see, for example, if I1 is known to me, refractive index is known to me, from just these two, using Snell's law, I can find R1. Now from R1, I can find R2 using the formula R1 plus R2 is equal to A. And how did I find this out? I found this out using Snell's law. Snell's law. Once I know R2, I can again, using R2 and using refractive index, using again Snell's law, I can find I2, which is the emergent angle. Then using our deviation formula, I1 plus I2 minus A, using this, I2 is known, I1 was already known to me, and angle of prism was already known to me. Using this again, we can find the deviation. So it's a very lengthy process if you notice. If you notice, for different angles of I want to find the different deviations. It's a quite lengthy process, but it is doable by calculations. You keep doing it for different angles, and you draw basically something like a graph. So here on the horizontal line, you draw the incident angle, and on the vertical line, you basically show the deviation angle. And for every I1, find what is delta. For every I1, find what is delta. You start drawing a graph. And you can do this experimentally also. And when you do this experimentally, or when you do it calculation wise, the answer is very simple. The answer comes out to be something like this. It looks like a U-shaped curve. It looks like a U-shaped curve with a point of minima. Means there is a point where minimum deviation happens. There is a point of minimum deviation. Definitely that happens. But mainly you should know the structure of the graph comes out to be something like this. You will also notice that there are certain angles for which the deviation is same, and it happens 2 times. The repetition happens 2 times, maybe 20 degree and 50 degree, the deviation is same. Okay, and you can see the deviation is same for two angles, and that happens for most of the angles except for when there is minimum deviation. You only will get a single angle. There are no two angles. That is what you will see. That is what you will basically see. Exactly. So when that happens, when basically that happens, the minimum deviation, you will notice that the incident angle and the emergent angle both are equal to each other. It will be a completely symmetric scenario. It will be a completely symmetric scenario. That means, however it enters at whatever angle, it exits also at the same angle. That means even the internal angles will be equal. Not just that, this refracted ray inside the prism will be parallel also to the base. So this entire diagram I might have to change. This entire diagram I might have to change because the ray will be looking slightly differently, and we can do that. There is no harm in that. So probably we'll just remove all of this. Okay, let me. Oops. Wow. Okay. Probably I'll have to do this again only. I can't do this here. Please. Can I just remove this? Remove this. Remove this. Okay. I will just put it back over here. And what I will show is basically once it enters inside, it is parallel to the base. And when it exits outside, it is exactly going to come out the same way as it entered inside. As simple as that. However, it entered inside exactly the same way. So you will see this particular angle over here, which is I1, will be exactly equal to this particular angle. Even this angle and this angle, R1 and R2, both of them will also be equal to each other. So in case of minimum deviation, in case of a minimum deviation, so I'll just write it down. For minimum, for minimum deviation, for minimum deviation, what and all things will happen? Incident angle will be the emergent angle. The internal angles will also be equal. The refracted ray inside, the refracted ray inside, the refracted ray inside is parallel to the base of the prism, is parallel to the base of the prism. All these criteria will be met for minimum deviation. Symbolically, I will put delta m. So now you might be wondering, sir, is there a formula that I can get for the minimum deviation? The answer is definitely. We can definitely get a formula for the minimum deviation. And let's see what is that formula going to be, because that is what we want. What is the condition for the minimum deviation? The derivation goes as follows. Observe this carefully, guys. Observe this carefully. Let's apply Snell's law on the first phase. Let's just apply Snell's law on the first phase, and according to basically Snell's law, on the phase number 1, I should be able to write sine of I1 divided by sine of R1 is basically mu. But I don't know I1, I don't know R1. So what I will do, I'll just think, can I use some formulas which I know? Well, I just know R1 plus R2 is A, but we also know R1 is R2. We also know R1 is equal to R2. So substitute R2 as R1. Therefore, R1 plus R1 is A. So 2 times R1 is A, or rather R1 is nothing but A by 2. Oh, perfect. Also, one more thing which we can write down. One more thing which we can write down using this. We can write down using this. I know that the minimum deviation is I1 plus I2 minus A. I1 plus I2 minus A. But I1 is equal to I2. But I1 is equal to I2. So therefore, I1 plus I1 minus A, that is what is delta. Shift that A on the other side. shift that A on the other side. Let's see what do we get. We will get delta plus A. This only will happen for minimum deviation. This will only happen for minimum deviation is 2 times of I1. Rather, I1 will be nothing but delta minimum plus A whole thing divided by 2. Oh, I got I1. I also got R1. I think now I can substitute. I'm ready for it. So let's substitute and see what do we exactly get. So mu will be equal to sine of something upon sine of something. So what is that sine of something and sine of something? Sine of I1. I1 we just saw it is nothing but delta m plus A divided by 2. And what is R1? R1 is nothing but A by 2. So I can just put over here A by 2. Perfect. I've just derived a formula. The refractive index is related to the minimum deviation using this formula. Using this formula. Okay. Begin. The notes are uploaded on the Jungle Book. Yes, already uploaded. Okay. Awesome. Awesome. Uh, Outside the prism is, yes, it's his rarer medium. Yep. Yep. Okay, great. And yeah, regarding the portion of the test series, I'll be uploading it by today, maximum tomorrow. I have got that. We are just arranging it in a proper way so that we can send it to you. I'll be sharing it on the Telegram channel. Okay, don't worry. I'll be sharing it. So finally, what is the condition for minimum deviation? The answer is mu is equal to sine of A plus delta minimum by 2 whole thing divided by sine of A by 2. This is the condition. This is basically the condition for minimum deviation. Okay, this is what we have just derived. So all these are very, very important formulas, whatever we have learned till now. Okay, right from the beginning. Right from the beginning, what is the angle of prism? What is the meaning of prism? How R1 plus R2 is A. Then we also saw how we can apply Snell's law. Then we also saw the total deviation formula is I1 plus I2 minus A. Then we saw how you generally plot the graph of incident angle versus the deviation by calculation or by experiments. And then we saw the condition for minimum deviation and we then obtained a beautiful looking formula. Okay, so these are the main formulas of a prism. So let's start doing some questions now. Okay, ready for it, my dear warriors? Let's start doing some questions. Look at this. The angle of minimum deviation for a prism is 30 degree. The angle of minimum deviation is 30 degree. The angle of the prism is 60 degree. Find the refractive index of the material of the prism. Let's see what and all is given to us. We have been given delta minimum is basically 30 degree. The angle of the prism is given to be 60 degree. We have to find refractive index. Perfect. I know delta m A, delta m A. Yes, I think we should be able to find refractive index without any issues. So mu will be sine of A is 60 plus delta minimum is basically 30. Whole thing divided by 2. Whole thing divided by sine of A by 2. Angle of the prism is 60 by 2. That's it. So 60 plus 30, 90, 90 by 2 is 45. So this will be sine 45 degrees upon this is nothing but sine of 30 degrees. Sine 45 is 1 by root 2. Sine 30 is half. So it will become 2 divided by root 2, which is root 2. What's the value of root 2 approximately? Well, it is 1.414. So that is the refractive index of the prism. As simple as that. Is that okay? Yep. I hope this is clear. I hope this is absolutely clear. Everyone, shall we go ahead? Shall we go ahead to the next question coming up on your screen? A prism having refractive index root 2 and reflecting angle 30 degrees has one of the refracting surfaces polished. Interesting. A beam of light which falls on the other refracting surface will retrace the path of if the angle of incidence is how much? I think we'll have to draw the diagram. Without the diagram, we cannot proceed. So let's draw a diagram. This is our prism. Okay. The beam of light incident on the refracting surface retraces, assuming the refracting surface is polished. That means this surface is behaving like a mirror. This is like that polished surface. This is like that polished surface which behaves like a mirror. On a mirror, if you remember, the concept goes like this. The concept goes like this. If light falls at an angle, it will reflect at some other angle. Only if it falls vertical, it will retrace back the same path. So only when it falls normal to the surface, it retraces. It basically retraces the same path. That means the incident ray should be normal on this. That means the incident ray should be normal on this. Okay, so it should be normal on this. Perfect. No issues. At this point, it will probably refract. At this particular point, probably it will refract. And maybe we can just say the angle is looking something like this. Okay, so this is how the ray diagram would look like. Let me show the arrow marks. It will go like this. It will also go like this, but it will again rebound back same way. This angle over here is 90 degree. Okay. The prism is having a refractive index of √2. So the refractive index of the prism is √2. Perfect. That is also given. The reflecting angle is 30 degree, means this particular angle over here is 30 degree. That is what they mean. The reflecting angle of the prism or refracting angle actually should not be reflecting, it should be refracting angle. So the refracting angle is basically 30 degree. Hi Gunjan, welcome. Hello Poonam. Yep. Okay, great. Now, if that is 30 degree, can someone tell me how much will this particular angle be? Can someone tell me how much will this particular angle be inside that particular prism? Think carefully and answer. How much will this particular angle be for this right angle triangle? This is 90, this is 30. Obviously, this will be 60 degree. If this angle is 60 degree, can you quickly think and tell me how much will this particular angle be? How much will this particular angle be? Obviously, total is 90. So hence, this must be 30 degree. Very nice. So we got 30 degree. And I want to find out the angle of incidence. That means this particular angle is what I'm looking for. Now I just use Snell's law, and using Snell's law, sine of I divided by sine of 30 will be refractive index. So therefore, sine of I is mu. Mu is basically root of 2 multiplied by sine 30, which is nothing but half. Sine 30, I just take it on this side. So this is nothing but 1 by √2. So think about it. Whose sine is 1 by √2? It is 45 degrees. So hence the angle of incidence must be 45 degrees. Perfect. Yes, that is the correct answer. Let's find out. Yep, it is 45 degrees. So if you notice in prisms or in general ray optics, most of the times you need some geometrical theorem, property, axiom, right, formula, somewhere or the other. You need either angles, parallel lines property, triangle property, quadrilateral property. So if you're good with geometry, ray optics becomes easy. I won't say it will become a cakewalk, but it becomes easy because then you don't have to think too much about, oh, what will this angle be, what will that angle be, etc. All right, let's move to another question coming up on your screen. This was asked in JEE Mains 2024 this year, and it got repeated 2 times. If you notice, pi is 180. First time it came in terms of radians. Next time it came in terms of degrees. It's basically the same thing. Instead of pi by 2, they have put 90 or something like that. So they just changed the options also slightly here and there. Other than that, nothing much has changed. So question is, what is the angle of minimum deviation? Question is basically, what is the angle of minimum deviation? If the apex angle is A and the refractive index of the prism is cot of A by 2. Interesting. I feel we should stick to our original formula, which is mu is equal to sine of A plus delta minimum by 2 divided by sine of A by 2. Now this mu is given to be cot A by 2. Cot is cos by sine. Cot is nothing but cos divided by sine. So let's use that over here. So it is cos of A by 2 divided by sine of A by 2. This is equal to sine of A plus delta minimum by 2 whole thing divided by sine of A by 2. Interesting thing to note is that this sine A by 2 and this sine A by 2 will cancel, right? And what will you get? Cos of A by 2 is this. So cos of A by 2 is sine of A plus delta minimum by 2. But I can't compare cos on sine like this. So instead, what I will do is, I will just write cos as sine of 90 minus a by 2. Is that fine? 90 minus a by 2, because sine of 90 minus theta is cos theta. Oh, now I think it is comparable. Now I think it is comparable. So 90 minus a by 2 is equal to a plus delta minimum by 2. Take LCM. So this will become 180 minus a whole thing divided by 2 is a plus delta minimum whole thing by 2. 2 cancels. 2 cancels. So shift a on the other side. Shift a on the other side. So it will become 180 is equal to 2a plus delta m, or what did I want? I wanted minimum deviation. Okay. So in fact, we'll shift a on the other side. My bad. Let's shift a over here. So it will become 180 minus 2a is equal to delta minimum. So delta minimum is 180 minus 2a, which is right over here. In this case, in 31st January shift number 1. And in this case, 27 January shift number 1, this should be the correct answer. Let's find out. Yes, this and this were correct. This was repeated 2 times in this year. Yep. Vaishnavi, don't spam. Yep, you can. Please watch my strategy video on how should be your monthly planner be. It is there on this channel only. Okay. You don't have to go anywhere else. It is there on this channel. Just go to, where is it? Go to videos. Simple it is. I have given a proper plan, full syllabus in less time, how to clear the backlogs. That is number one thing which you need to watch. And in the live class, I think I have given that proper strategy of what and all things you need to do. Proper roadmap. Okay, just this was for droppers. I have given it for freshers also. Proper roadmap I have given what you should do. Just watch it. June month is over, but still you can use the same strategy video. Okay, right. Shall we go ahead to the next question coming up on your screen? Here it comes. What does it say? The refractive index of a liquid filled in an equilateral hollow prism is √2. Angle of minimum deviation for the liquid will be in an equilateral. What is delta minimum if the angle of prism is for an equilateral triangle? Oh, it's an equilateral triangle, guys. Come on. So A will be basically 60 degrees. Mu given to be √2. Delta minimum is the question. All right. So let's use our formula. Refractive index is sine of A plus delta minimum by 2. Whole thing divided by sine of angle of prism by 2. That's clearly mentioned equilateral. That's why angle of prism is 60 degree. Shift this over here. So therefore, √2 multiplied by sine 60 by 2 is sine 30, which is nothing but sine of 30 is equal to sine of 60 plus delta minimum by 2. Sine 30 is half. √2 into half. Sine 30 was just half. So it will just become 1 by √2 is sine of this entire thing. Whose sine is 1 by √2? Basically 45 degrees. So therefore 60 plus delta minimum by 2 will be nothing but 45 degrees. Perfect. So multiply 2 with 45. What will I get? 60 plus delta minimum is nothing but 90 degrees. Okay. So therefore, delta minimum will be 90 minus 60, which is nothing but 30 degrees. So the correct answer to this question will be 30 degrees. What a amazing question, guys. This was asked in JEE Mains, right? How to know this formula to be used? You know what is given. A is given, mu is given, delta minimum is asked. There is only one formula in the entire set of the prisms which has only these three variables. There is only one formula like that. All other formulas have other unnecessary things like I1, I2 and A. All these unnecessary things are there. Okay. So those things will not be needed. That means you need only this formula. So this is a major formula in this entire question. Okay. Now let's move on to the next concept of thin prism. What do I mean by thin prism? Very simple, guys. The angle of the prism should be very small. Something like this. The angle of the prism should be very small. That is basically called as a thin prism. So angle A is very small. And once the angle is small, what happens? Think about it. You can use trigonometrically small angle approximation formulas, correct? You can use small angle approximation formulas. Not just that, there is one more interesting thing which happens. Let me show that as well. You will see that this particular graph, which I had shown for different angles of incidence versus deviation, for a normal thick prism, it is like this. This is for a thick prism, or when angle A is basically large, when the angle is large. But the moment the angle is small, like the one here, you will see that the graph is almost flat. It is curved, but the curviness almost goes off, and you will see that the graph is probably something like this. That means whatever minimum deviation you get is almost the deviation for almost all the angles. So for thin prism, the deviation is almost the minimum deviation for all angles, I1 of, or I can just say for all angles of incidence. For all the angles of incidence, the deviation is almost going to be the same. This is when I1 is equal to I2. It's almost going to be the same. This is a very interesting thing. So I don't have to worry whether minimum deviation is occurring or not. It will roughly be the same. That is so amazing, which we can use it for solving problems. Okay. So now, if I have a ray of light and it refracts and again refracts over here, and there is some deviation which is occurring, I want to find how much that deviation is. Obviously, this deviation won't be too huge. Don't expect this deviation to be very large, guys. Why? Because angle is very, very small. Delta is also very small. Delta is also going to be small, like 10 degrees, 5 degrees, 4 degrees, 0.1 degree, like that. It is not going to be like 70 degrees or 50 degrees. So what do we do now is that, let me just put it on the next slide over here, that small derivation. Since we know mu is equal to sine of a plus delta minimum by 2 divided by sine of a by 2, using small angle approximation formula, mu will approximately now be equal to, instead of sine of this, I can just put the angle. Sine theta is theta. So I can just put a plus delta minimum divided by 2 by a by 2. 2 cancels. Therefore, mu will be equal to a plus delta minimum divided by a. Shift a on this side, so it will become mu times of a will be nothing but a plus delta minimum. Now shift this a on the other side, so therefore I will get delta minimum will be mu times of a minus a. Therefore, delta minimum will be a common, mu minus 1. Amazing formula. The deviation is a into mu minus 1. A into mu minus 1 for a thin prism. And it will be not just minimum deviation, it will be all deviations, because delta minimum is delta. Therefore, I can then generalize it. Therefore, I can also generalize it that the deviation is a into mu minus 1 in general, not just minimum deviation. It's for all the deviations. Very, very important formula. Thank you, Divakar. Thank you, Warrior Pandus. Okay, clear, everybody? Shall we proceed ahead? Shall we proceed ahead now? So there could be some questions like this. I've seen a question like this where there was a thin prism given. And in front of the thin prism, there was a mirror which was given. Okay, and it was given that you know, in this particular example, without the prism, without the prism, okay, the ray retraces the path after reflecting from the mirror, after reflecting from the mirror. With the prism, with the prism, find the deviation, find the deviation after reflection with respect to the incident, with respect to the incident ray. This is the question which was asked. Let's try and understand what it actually means. See, when that prism is not there, assume this prism is not there, then if a light ray falls on the mirror, then it retraces that path. That means it was normally incident. Now what has happened is you have a prism on its way. You have a prism on its way. So ideally, this ray should have gone straight, but because of the prism, it will get deviated. Ideally, it should have gone like this, but now it will get deviated for sure. So how will it get deviated? We all know that because of that prism, let's say some mu values, etc. are given to me. This angle of the prism is, let's say, something like uh, 3 degrees or something. And let's say, um, this is having a refractive index of 1.5 or something. Okay, you can just take 3 degrees and 1.5 is the refractive index that is, let's say, given to me. So this ray will 100% inside the prism get deviated. It will get deviated like this. You can see how the prism is placed. So it will probably get deviated like this and it will go here. So how much will this particular deviation be? How much will this particular deviation be? Can we figure that out? Can we figure that out? Yes, why not? So that delta 1, if I write it down, using the thin prism formula, A into mu minus 1, which is nothing but A into mu minus 1, which is 3 degrees, 1.5 minus 1, which is 3 into zero point 5, 3 into 0.5, right? So which is half. So it is just nothing but 3 by 2 degrees. So delta 1 is nothing but 3 by 2 degrees, or basically you can just call it as 1.5 degrees. So when it hits the mirror, it will not hit at 0 angle of incidence. So at this particular point, if you draw a normal, you will easily see even this angle, which is the angle of incidence, because these two lines will be parallel. Also, I will say this angle will be equal to this delta 1. These are alternate angles, so they should be equal. Therefore, that angle should also be 2, or basically 1.5 degrees. Everybody agrees with this? This should be also 1.5 degrees. So after this, what will happen? This same ray is going to get reflected and it will go like this. So 100% now there is a final deviation. Now there is a final deviation which occurred, the delta 2. So how much will that delta 2 be? How much will that delta 2 be? Well, that delta 2 using mirror formula, 180 minus 2i. So 180 minus 2i. What is 2i? 2 into 1.5, which is 180 minus 3 exactly. So it will be 177 degrees. It will be nothing but 177 degrees with respect to that incident ray. Everyone with me? Everyone with me on this? But you know what? This is not the actual answer. Can somebody tell me why this is not the actual answer? Can somebody tell me why this is not the actual answer? Think about it. Read the question carefully. Read the question carefully. find the deviation after reflection with respect to the original incident ray. This was our original incident ray. Be careful. So with respect to this, it has deviated so much. It has deviated so much. But it already deviated delta 1 here, right? It has already deviated delta 1 here, and then further deviation occurred. Do you see that? So hence, if I have to find the total deviation, it will be 177 plus that original deviation, which is 1.5 degrees. Therefore, the total deviation, did you understand? We had to measure the deviation with respect to the incident ray. So you have to add plus 1.5, only then it will become 178.5 degrees. So hence this is the correct answer. What a question this is. So guys, this question definitely deserves some bit of appreciation. I just won't call it example. I should probably call it a level 2 or level 3 question. Level 2 or level 3 question. Correct? Understood this question, guys? What a question this is. Okay. So this is how you can use this particular concept along with a mirror. Let's move to some more questions, but for that, let's just study dispersion of light first, and then we can see some more questions of application of that particular formula. Say, what is dispersion? It is not the same as scattering. A lot of people get confused between scattering and dispersion. Scattering of light is when light falls on different molecules, atoms, dust particles, etc., and it scatters everywhere. And we see that, you know, our sky looks bluish, violetish, all right, because of the scattering effect. Because of the scattering effect, the oranges, the reds, they get scattered, right, and differently as compared to the blues. That's why we end up seeing our sky as blue in color. Now, dispersion is the difference of the deviation or the refractive index which causes the splitting up of light, that causes the splitting up of a light when the medium changes. Okay, so scattering was with regards to falling on dust particles and getting scattered everywhere, reflecting everywhere. Dispersion is splitting up of colors when the medium changes, because the deviations are different for different colors, or the refractive indices are different for different colors. The best example is right over here. You pass in white light through a prism, you will see by the time it comes out, you will see different colors which actually make up the white light. Understand, white is not a color. White is not a color. Think about it. It's a mixture of colors. Your brain fools you to think it is white. Actually, white does not have a wavelength. It's a mixture of all these colors: violet, indigo, blue, green, yellow, orange, red. Vibgyor colors. Brown is not a color. Pink is not a color. Magenta is not a color. Teal is not a pure color. These are basically combination of different colors in different proportions which your brain perceives as something. Exactly. So, my dear students, the dispersion basically breaks up your original color and makes you realize, oh, you know what? These were the colors making up that original color. So if you pass brown, maybe you might get some 2-3 colors here. If you pass maybe pink, you might get some different colors over here. Whatever colors make up that original thing, you will see they will be split up. That is basically dispersion. That is basically dispersion of light. I hope the concept of dispersion is absolutely clear. It's a phenomenon of separation of different constituent colors of light while passing through a medium. Okay, when the medium changes, you will see they will split up. Now, looking at these diagrams, it is very, very obvious who spreads the most or who deviates the most, etc. So, guys, if I probably, yeah, don't have purple on. Okay, so if you really ask me who deflected the most in this, that will be violet. Who deflected the most, that will be basically violet. don't have violet exactly, I'll just use this color. So deviation of the violet color is the most in comparison to everything, because you see violet color has deflected the most. Then you see blue, then green and all that. The average of all of them is called yellow. So delta yellow is slightly less. And the least of them is the red color. The least of them is basically the red color. So this also means the refractive index of the red is the least. Slightly more than that is the refractive index of yellow color, and the highest of them all is the refractive index of violet color. This is also called as mean color. Yellow is also called as the mean color. The mean color is for white light is nothing but yellow, is nothing but yellow. Keep this in mind. Very, very crucial again. Now, this also means one more thing. If I want to find the deviation of violet color, I will just write mu violet over here. If I want to find deviation of yellow color, I'll just write mu of yellow over here. If I want to find the deviation of red color, I'll just write mu red over here. The rest of the things just follow as it is. It will be A into mu minus 1, A into mu minus 1, A into mu minus 1. So if you know the refractive index, you can find the deviation. If you know the refractive index, find the deviation. So every color has a slightly different refractive index. Now tell me one thing, when they tell you the refractive index of glass is 1.5, which refractive index are they exactly referring to? Are they talking about the red color, yellow color, violet color, or something else? Because every color has a different refractive index. Infrared will have slightly different, ultraviolet will have slightly different. So when they give you any refractive index, for water it is 1.33, for diamond it is 2.4, which exactly they are talking about? What exact refractive index are they referring to? Which color are they referring to? My dear students, they are exactly referring to, yep, yellow color. So whenever they give the refractive index, it's always for yellow color. Keep that in mind, which is the mean color, which is the average color. Honestly, no problem. You can still continue. We are just started with dispersion. I'm pretty sure you will be able to catch up. Whatever part you have missed, you can watch it later on. Also, this means one more thing. Keep this in mind. The refractive index of the yellow color is actually the average, of the violet color and the red color's refractive index. This is also very, very important. If I know this is 1 point something, this is 1 point something, I take the average, I will get the refractive index of the yellow color. It's truly the mean or average. So you take numbers, you find the average, exactly it is the mean. That is why also it is called as the average color or the mean color. Yep. I hope this is clear. ProCuber, I'm already using Nurture series. Should I watch this or stick to Nurture? ProCuber, I would suggest whatever lectures are going live over here, stick to this current class, because obviously this is live and I'm using some different set of problems. But if there is some test in your school, or let's say in your coaching, or maybe you are having a certain plan and you feel that, okay, sir, I want to study this chapter, but you are not yet teaching that, maybe you will teach it after a few weeks. So then use the Nurture series. Very simple. Okay. So if some class is live, I would suggest watch this. No need of old class, although those classes are also excellent. Okay, so it's up to you which class you want to use, but I would suggest use these live classes. If there is a topic in need, watch those Nurture classes. Yeah. All right. Cool. Now, moving ahead, moving ahead, moving ahead. Let's talk about angular dispersion. Very, very important. Let's talk about angular dispersion. Oops. This is our prism. White light entered over here and then it started splitting. We know violet, oops, we know violet will deviate the most, whereas red will deviate the least. Now, if you extend them backwards, maybe. Over here. Something like this. This was the original path. These rays have got deviated. So let's see here. This is nothing but deviation of the red color. This thing over here is nothing but deviation of the violet color. If you notice, the final rays are not parallel to each other. Rather, they have some angle between them. Okay. So that spread of that angle, whatever you are seeing, this particular spread of the angle, I can call it delta theta, which is called as the angular dispersion. The spread of the constituent colors, the spread of the constituent colors is called as how much angular dispersion which is there, which is given a symbol delta theta. Naturally, delta theta which is there, easily you can see it is nothing but delta of violet minus delta of red. Delta of violet minus delta of red will be the remaining angle. How much is delta of red? It is angle of prism into mu of red minus 1. How much is delta of violet? Angle of prism into mu of violet minus 1. If you remember, these formulas are also over here. Exactly the same thing. These are for thin prisms, assuming. Now what will happen? A and A will get cancelled. A and A will just get cancelled. So therefore, delta theta will be, you can notice, A will be also common. A will also be common, and we will be just left with mu violet from here, and we'll be left with mu of red from here. So this is the angular dispersion. How much is the spread? Again, a very, very important formula. Angular dispersion is angle of prism into the difference of the refractive index. Or better to remember this, which is very, very simple. If you know the diagram, you don't even have to memorize it. If you know the diagram, if you know how things work, you don't have to even memorize this. It is understood. It will be the difference of the deviation. Difference of the deviation means A into difference of the refractive index. As simple as that. So you don't have to remember much if you understand things how they work. Or else you will think, sir, this is difficult, sir, this is that, this is this. And when you practice more problems, you will automatically remember it also. Remember that. Okay. So this is something which we have done. Is a difference of the deviations or the spread, angular spread. Next thing what you get is something called as the dispersive power. Next thing that you get is something called as the dispersive power, where you will see your final rays are something like this. This is the violet ray. This is the red one. The yellow one, which is the average, is like this. So your yellow color, okay, as compared to the original ray of light, your yellow color has deviated by some amount, and there is some angular spread over here. There is some angular spread over here. How much is that spread with respect to the deviation of the mean color? That is called as dispersive power. So what is dispersive power? Let's write it down over here. Dispersive power. Dispersive power is nothing but your angular spread or angular dispersion, how much ever is that angular dispersion, divided by the deviation of your mean color. Deviation of your mean color. The symbol for dispersive power is generally omega. Angular dispersion delta theta, and mean color deviation is nothing but delta of yellow. This was yellow. Okay, that's it. Omega is delta theta by delta of your yellow color, which is the mean color. Exactly. So this is nothing but dispersive power. Now you can find this out. It's not that difficult. Okay, you can just write delta yellow as A into angle of prism into refractive index of yellow minus 1 over here. Then what is delta theta? Delta theta, if you remember, it was nothing but angle of prism into mu violet minus mu of red. Exactly. So A will get cancelled. So therefore, omega will be nothing but mu of violet minus mu of red, the whole thing divided by mu of yellow minus 1. That's it. That is what the final formula is. This is for yellow, this is for violet, and this is for your red. That's it. That's the formula for the dispersive power. This is for the dispersive power. Okay, everyone? All right. Are these formulas only for thin prism? Yes. All these formulas, whatever you are studying, okay, whatever we are studying over here, in general, are for thin prisms, because remember, these formulas, like I told you just some time back, they are only for thin prisms. Where did we go? See, this was only derived for thin prisms, A into mu minus 1. If it is not thin prism, then you have to calculate it using a lengthy process. As simple as that. Okay. Let's see if you guys can figure out some questions, answers. Here is the first question. Is dispersion possible in a hollow prism? Very interesting question. Actually, this is there in the Tattva module. Okay, it is there in the Tattva module. A very different question. If you're having the Tattva module, you can open it up right now also and see in the Tattva module, you're going to find this question. So, by the way, Tattva has 4 levels of questions. Level 1, level 2, level 3, level 4 with PYQs and solved examples and theory notes and solutions along with video answers. If you scan the QR code. Okay, so if you are using it, use it to the fullest. Some of you are probably not even aware, sir, what is that QR code for, sir? The QR code is for scanning and seeing the video solutions and even video concepts on that particular topic. Okay. Think about it. What do you think might happen? What do you think might happen for a hollow prism? I feel nothing will happen. You know what? There will be no dispersion only, kind of, because both the faces will behave like glass slabs. Just look at this face. Just look at this face. It is like a glass slab, and I just spoke about glass slab some time back. I just spoke about a glass slab. So whenever you have a glass slab, what happens? Whatever ray will come, it will just get laterally shifted. It will just get laterally shifted. There is no deviation only. The deviation is 0. So even on the other face, when that same ray will go, it will probably, okay, deviate inside, but again when it comes outside, it will just get laterally shifted, but the deviation will be 0. So there is no deviation for any color. There is no deviation for any color. So there will be no angular spread, no dispersion, no angular dispersion, no point of measuring dispersive power also. So there will be no dispersion at all. Yes. So understand that. So why it is happening also you should know. It is because both the faces will behave like a normal glass slab. As simple as that. Okay, let's go to the next one. When white light passes through a glass prism, one gets the spectrum on the other side of the prism. In the emergent beam, the ray which is deviating the least is, or deviation by a prism is lowest for which? For which of the rays the deviation is least when it passes through a prism? I think the framing, some grammar mistake is there, but basically they're asking for which color, the deviation is the least. Come on, my dear students. Violet deviates the most. Vibgyor, violet, indigo, blue, green, yellow, orange, red. So red should be the answer. Yes, red is the answer. No, it is not violet. For violet, the deviation is the most. For red, the deviation is the least. Exactly. I just showed you the diagram. Remember this? Violet, indigo blue, green, yellow, orange, red. You have seen this. Even look at this diagram or this diagram. Everywhere. Violet is the most, red is the least. Always. Keep that in mind. Okay. Let's go to the next question coming up on your screen. The refractive indices of red and violet color are this and this. You can see two different values, but very close to each other. Changes are in the second decimal place onwards. Find the angular dispersion produced by a thin prism of flint glass having a refracting angle. Find the angular dispersion. That is what the question is. Come on. First of all, what will you do? First of all, what will you do? Do you know the formula for angular dispersion? Yes. Delta theta is nothing but A into mu of violet minus mu of red. So what is angle of prism? It is just 5 degrees. What is refractive index of violet? It is 1.632 minus this is 1.613. Everybody with me? Understanding? I'm just using the formula, nothing else. Nothing else. Exactly. Cool. So what is it that you will get? 32 and 13, that's just 19. So that will be nothing but 5 degrees multiplied by 0.019. So how much is it? 19 fives are, guys. 19 fives are. Yes, 95. So it will be 0.0.095 degrees. So that is your delta theta. As simple as that. How many of you got it? How many of you got it? 0.095. Yes, the answer is 0.095. Perfect. You got it. But sometimes, let's say the questions could be slightly different. The questions could be slightly different. Like for example, the question could have been, what is the refractive index of yellow color? Let's say this is also one of the question. What is the refractive index of yellow color? What will you do? You will just take both the refractive indices, add them and take the average, so divide by 2. So it will be 1.613 plus 1.632 whole thing divided by 2. Is that right? 1.613 plus 1.632 whole thing divided by 2. How much will it come out to be? Just check it out. How much will it come out to be? Come on. 1.613 plus 1.632 whole thing divided by 2. Just do it. 2 plus 3, 5. Yes. 3 plus 1, 4. Yep. Just check this out. Come on, my dear students. Come on, my dear students. 3.245 divided by 2. How much is it coming out to be? Yep. 6.28 is the average around. Find it out exactly. 1 point. How can it be 6.28? How can it be 6.2? Think about it. Think about it. Again, it will be 1.6 something, somewhere in between it will be. Yep. How much will it be? 1.6 between 13 and 32. Between 13 and 32. How much will it be? 6. Yep. This will be 2 2 5. Yes. 1.6225. That is the final answer. That will be the refractive index of the yellow color. Very good. Very good. If they ask you, what is the deviation of the yellow color? What is the deviation of yellow color? What will you do? Deviation of the yellow color. Use the angle of prism formula, which is basically 5 degrees into 1.6225 minus 1, which is 5 degrees multiplied by 0.6225. So that will give you the deviation of yellow color. Come on, multiply and see how much are you getting the deviation as. Multiply and see how much you are getting the deviation as. Come on, my dear students. 3.1125 degrees. Just check this out. 3.1125 degrees. Very good, Divakar. Very good, Dharani Shwaram. Very good. Very good. Excellent. So this is how you solve basically questions on prisms if angle of prism is given, refractive indices are given, etc. If they ask you dispersive power, if they now ask you what is dispersive power, which is omega, what you will do? You will take this and divide it with this. So it will be basically 0.095 whole thing divided by 3.1125. That you do, but you get the idea. If omega, which is dispersive power, is asked, you just divide angular dispersion by your deviation of the mean color, which is yellow color. As simple as that. Okay. So let's proceed ahead to another question which was asked in JEE mains. Thin prism of angle 6 degrees, refractive index of yellow is this, combined with another prism of angle 5 degrees, refractive index something else. Combination produces no dispersion. The average deviation produced by the combination is how much? If it is 1 by x degrees, find the value of x. Okay, the combination is producing no net dispersion. Interesting. And we are given both the refractive indices of both the prisms, including the angles. So what is the net deviation? What is the average deviation? Average is nothing but yellow. So we have to focus our entire attention on yellow color. And they have given for yellow color only here as well as over here. Perfect. Now, when you go through the first prism, think what will happen. When you go through the first prism, that yellow color will deviate this way. There will be a deviation like this, clockwise. When you go through the second prism, the deviation will happen like this, anti-clockwise. Once here, once there. Do you see that? And because they are in opposite direction, the total deviations won't add, rather they will subtract. Exactly. So hence I will say that the total deviation will be modulus of, I don't know who is more or who is less. So delta 1 minus delta 2, as simple as that. What is delta 1? What is delta 2? Okay, delta 1 is angle of prism into mu 1 minus 1 minus delta 2 is angle of prism into mu 2 minus 1. That's it. That is what your individual deviations are. All right. So how much will that be? Let's figure it out. What is the first angle of prism? It is 6 degrees, sir. What is refractive index? It is 1.5, sir. Okay, so 1.5 minus 1. What is the second angle of prism? It is 5 degrees, sir. What is the refractive index? 1.55 minus 1. Okay, just you have to find the modulus of this. So just figure this out, my dear students. How much is this coming out to be? How much is this coming out to be? 1.5 minus 1 is 0.5. 0.5 into 6 degree is basically 3 degree. Minus 1.55 minus 1, which is basically 0.55. And you have to multiply that with 5. How much will it be? 25 275. So it will be nothing but 2.75 degree. It will be nothing but 2.75 degree. Yes, 2.75 degree. Perfect. And I can clearly see 3 is bigger than 2.75. No need of modulus anymore. So hence it will be just 3 minus 2.75, which is basically 0.25 degrees. So hence 0.25 degrees should be the answer. Now 0.25 degrees, you have to write it in this form, which is basically 1 by 4th of a degree, which means if you compare this with this, our answer for x should be 4. Our answer for x should be 4. Exactly what we got. Exactly what we got. Everyone? Hello, SK Talks. So these are the kind of questions which you generally get. Now, remember, there could be always two combinations of prisms which you can get. There is one combination which looks like this, where your yellow color deviates and again comes like this, parallel to the original white light, If this happens, then the average color is not deviating, so there is no deviation. There is no deviation on an average, but there could be dispersion, meaning that red color might go like this, and it could probably spread like that, and our violet color probably might go like this, probably like that. So there is some bit of dispersion. Dispersion, dispersion is there. There is some dispersion, but no deviation. And when this happens, look at it, because the deviation is not happening anyhow. So whatever yellow color turned by in the first prism, same amount it turned in the second prism. So deviation of yellow color in our first prism will be the deviation of yellow color in the second prism. In the first prism, understand it is happening clockwise. It is happening clockwise. In the other prism, it is happening anti-clockwise. That's it. So these two deviations, magnitudes, if they are equal, if this is 3 degrees, that is also 3 degrees, total deviation will be 0 degree, because one is clock, other is anti-clock, just like in this problem. Here, they did not cancel out, so that is why there was some net deviation. There was some net deviation which we found out. If there was no net deviation, then you will see that both the deviations, clockwise and anti-clockwise, should cancel out each other. Is that right? And then there is another possibility which can happen. And then there is another possibility which can happen. Let's say you have a prism like this and something like this. Let's say white light falls over here. Let's go to red color. It goes like this, goes like this, goes like this, and it goes like this. Look at this particular diagram. The light deviated, it spread, again deviated in the other way, spread, but the final rays are parallel to each other and they are not even going in the same direction as the original incident ray. So in this situation, if you look at the yellow color, which is the average color, there is a deviation. The deviation is present. In this situation, the deviation is present, but what is absent is the spread. The angular spread is absent because the final rays are parallel. All the rays are parallel. So in such a case, there is no dispersion. So this is deviation without dispersion. There is no dispersion in this particular scenario. And when this happens, when there is no dispersion, but there is deviation, that means whatever angular spread was present, in the first prism, the same angular spread is also there in the second prism. It's just that they are cancelling. First it is expanding, and then again it is converging. So that is why they end up being parallel. So delta theta 1 will be delta theta 2 is the condition for that. Everyone clear about this? Everyone clear about this? Understood till this point? Can we go ahead now? Clear? Okay. Oops, we put this here. Let me just put this like this. Okay. Very, very important criteria. Let's take a 2-minute short break and return before we start off curved surface refraction. Let's just take a short break. Okay. Let's just take a short break of 5 minutes. We are going to start curved surface refraction. Yo, my dear students, my dear lions, are you able to see me, hear me loud and clear? Do let me know quickly in the chat box right now. Am I audible, visible? Hi, Dharneshwaran. Good evening. Once again, welcome back. It's time to start the next part of the class where we talk about lenses and curved surface refraction. All right. So, my dear students, curved surface refraction. What is this curved surface refraction? So many examples are there for curved surface refraction. Just one second. If you pour water in a test tube, the surface is something like this. If you pour water in a test tube, the surface is something like this. If you have seen a paperweight, it looks something like this. If you have seen a drop of water, looks like this. If you have seen, maybe a lens, which is again curved like this, a ray of light which passes through such a curved surface, a ray of light which passes through such a curved surface undergoes something called as the curved surface refraction. At the end of the day, at the end of the day, realize one thing, no matter which curved surface you are talking about, if you draw a normal to that curved surface at any point for that ray which is falling onto it, it will still obey our Snell's law. If this is I1, this is, or if this is I, and if this is R, I can still say sine of I divided by sine of R is 1 mu 2, or refractive index relatively. This is still obeyed. So Snell's law is obeyed at every single point for every single ray on that entire curved surface. So Snell's law is obeyed for all the rays, for all the rays, for all the rays, all right, and also for at every point, at every point. Keep this in mind, at every point. Is that absolutely very clear, my dear students? Okay, perfect. Now, we are interested in where this image is, how this image will look like, what's the magnification going to be, etc. So this is what we are going to see. Now, let's say for example, you have a curved surface, something like this, and we show a line which divides that curved surface into two equal parts. Then this will be our pole, this will be our principal axis. This curved surface obviously will be a part of a big sphere somewhere. So it will also have its own radius of curvature and also center of curvature. It will also have its own radius of curvature and center of curvature. Maybe this side there is a medium called mu1. Maybe on this side, let's say there is a medium called mu2. Now, if you have any object anywhere, if let's say this is our object, there will be multiple rays which will come out from it. There will be multiple rays which will come out from it. Maybe one ray here, then maybe one ray here, then maybe one ray here, like this. So many rays will be coming out from that object in different places. They will all undergo refraction on this curved surface. With respect to normals, you can find incident angles and the refracted angles. If you apply Snell's law properly, and then you see where these rays go and meet, maybe, I don't know, I'm just saying maybe they go and meet over here, or maybe they go meet here. I'm just chuma drawing it somewhere. Okay, just chuma drawing it somewhere. These rays are going like this, and probably, meeting over here. So they are all meeting at this particular point. So that means at this particular point, image will be formed. If they happen to diverge somewhere, you extend it backwards, you will get the virtual image location. So now I know by drawing the ray diagram, if I know where the object is, I can find out where the image is. I can also find the nature of the image depending on whether the rays are converging or diverging. At all the points, all I have done is I have applied our Snell's law. So Snell's law is applicable everywhere. Okay, so naturally, this will be our object distance. This will be our image distance. This will be our image distance. So if I know u, I can find v if I know mu1, mu2 and radius of curvature. Everybody agrees with this? Everybody agrees with this? Okay. How much is this? That is what we are interested in. Okay. We'll find that out in a bit. But before that, about the sign convention. Remember, in the ray optics first class, I already told you for curved mirrors, convex and concave, that wherever the light goes, that side becomes positive, the other side becomes negative, the pole is the origin. The same logic even applies here. If an object is here, the light from the object is coming this side, then this side will become positive, this side will become negative. If the light is coming from the other side, then the pole is the center, the origin. So this side will be positive, that side will be negative. As simple as that. So in all these cases, this will be the positive axis. This will be the positive axis. Light is coming from there. So this part onwards will be positive axis. This part onwards will be the positive axis. Whereas here, this will be the negative side. Oops, I think I showed from the wrong point. This will be the entire negative axis. This pole being the origin. This is the negative side. This whole thing is the negative side. Is that absolutely clear? So the direction, I'll write it down over here. The direction of incident light is towards the positive side of the pole which we consider, which is taken as the origin. The pole is always taken as the origin. This is our origin, pole. This is our origin. This is our pole. This is our origin. So now, if our curved surface is like this, the center of curvature is here on the positive side, so radius of curvature is positive. If the curved surface is like this, for this scenario, you will see the center of curvature is on the negative side, so R is negative. Here, again the center of curvature, because this is the curved surface, so the center will be somewhere here because this will be the sphere, imaginary. So center of curvature is negative. For this scenario, you will notice center of curvature is again positive. So depending on the direction of light, your center of curvature can lie on the positive negative side. So radius of curvature can also change the sign for the same diagram. You can see for the same diagram, if the light comes from here versus it comes from here, the sign of R can change. The sign of R can change just by the direction of light. So keep these things in mind. Keep these things in mind. Not just that, the object distance, image distance also get calculated by the same convention. So say for example, I have placed the object here, it is positive. If I place the image is over here, it is negative. If I see the object is placed here, negative. If I see the image is formed here, again negative. If I see the object is here, image is here, both will be positive. If I see the image and the object both are here, both will be negative. So object distance, image distance follow the same rules just like before. So if you look over here in this scenario, you will see that the light is going this side. So this side will be positive, this side will be negative. So the image will be having positive value. V will be positive, radius will also be positive because center is on the positive side. Object distance will be negative because it is on the negative side of the origin. Incident rays were going that side, not this side. It was going that side. So that is positive, this side is negative. Is that absolutely clear? Same rules apply. So what is the formula? What is the formula for finding image distance and object distance? It's very simple. See, you will remember mirror formula, 1 by V plus 1 by U is equal to 1 by F. It's very similar. You will see for lenses, it becomes 1 by V minus 1 by U. For lenses, it becomes 1 by V minus 1 by U. is equal to 1 by f. You don't have 1 by f over here. You first put v and u. What comes in the numerator and denominator? Very, very important. Sorry, what comes in the numerator on both sides? Here, what you get is the refractive index, where refracted rays, where the refracted ray is. Where is the refracted ray? Here. What's the refractive index? 𝜇2. So hence, this will be 𝜇2. This will be basically 𝜇2, where the refracted rays. What comes on this side is basically 𝜇1, but how do I write it down? It's the refractive index, where our incident ray is. That's what comes over here. So our incident ray is in this medium, so 𝜇1 will come here. The same order you follow here, 𝜇2 minus 𝜇1. 𝜇2 minus 𝜇1. Same order you follow over here. And in the denominator, you will just put the radius of curvature. You will just put the radius of curvature. So this is your curved surface refraction formula. This is your curved surface refraction formula. As simple as that. Okay. I have just talked about sign convention just some time back. No need for this slide. We just did this. Yeah. So this is your curved surface refraction formula. 𝜇2 by v minus 𝜇1 by u is equal to 𝜇2 minus 𝜇1 by r. Now you might be wondering, sir, is there a magnification formula also? The answer is yes. I'll give that also to you. Many books skip that particular formula. First of all, let me block this. Is there a magnification formula? Let's see what that magnification formula is. So, my dear students, for magnification, the lateral magnification, the formula is, which is image height by our object height. What was it normally for a mirror? It was negative V by U. For lens, you will see later on, it is plus V by U. Okay, so I remember it is V by U. Okay, I remember it is V by U. Image distance by object distance. Perfect. Who is coming with V? 𝜇2. Who is coming with V? 𝜇2. So just divide it with 𝜇2 over here. Who is coming with object distance? 𝜇1. So just divide this with 𝜇1. That's it. That is the magnification formula. Very, very easy trick to remember the magnification formula. V by 𝜇2 by U by 𝜇1. First, you remember V by U. There is no negative sign here. And then see who comes with V? 𝜇2. Who comes with U? 𝜇1. That's it. Just divide them. You will get the correct answer. As simple as that. Yes. Which is magnetism and matter from your lectures? I think you have to see something called as permanent magnets and magnetic properties and bar magnets. So those sessions from my old Pathfinder or Nurture series, that is what you will see. Okay. Right. Clear to this point, shall we do some questions? Let's do some questions based out of this. Sign convention also you have realized now. Okay, so let's have a look at some questions. Here is the question. This is there in H.C. Verma as well. Okay, locate where the image is going to be. I don't need this diagram. Find where the image is formed. Look at this curved surface. Object is placed 15 centimeters here. Center of curvature from the pole is 30 centimeters. Refractive indices are also given. Let's first think. The pole is just going to be this one. The pole is exactly this one. This is the pole. Okay. The object's rays will come like this. So that side will be positive side. So 100% I will take this as my positive axis. Naturally, this side will be our negative side by convention. Okay. Now, if I have to use our original formula, which is nothing but 𝜇2 by V minus 𝜇1 by U is equal to 𝜇2 minus 𝜇1 divided by R. Let's understand who is 𝜇2. 𝜇2 is the refractive index where the refracted light is present. The light goes like this, gets refracted here. So here the refractive index is 1.5. So 𝜇2 is nothing but 1.5. Image distance, that's exactly what I have to find out. Okay, we have to find where the image is. Minus 𝛎1. 𝛎1 is where the incident rays. The rays from the object go like this before getting refracted. So this is the incident. Incident is present here. So 𝛎1 is nothing but 1. Object distance. It's 15 from the pole, but on the negative side, so minus 15 is equal to, remember, same order has to be followed. So 1.5 minus 1. Radius. Radius, for that you look at center. Center is on the positive side, plus 30. So you just put plus 30 over here. Did you understand how we substitute the formula? How we substitute in this particular formula, my dear students? Awesome. Okay. All right. Now, you just solve this. 1.5 is basically 3 by 2 V. Take this on the other side. First of all, 1.5 minus 1 is 0.5. 0.5 is half. So it is 1 by 2 into 30. Minus minus is plus. When you take it on the other side, it will again become minus 1 by 15. Okay. So this will just become 1 by 60 minus 1 by 15. LCM is basically 60. So this is 1. 15 goes with 60 4 times. So this is 3 by 2 times of V. Okay. Let's see what do we get next. 1 minus 4 is basically minus 3. So 3 by 2V is equal to minus 3 by 60. Now you can obviously see this 3 and this 3 cancels. This 2 goes with 60 30 times. Okay. So therefore 1 by V is equal to minus 1 by 30. Therefore V is equal to minus 30 centimeters. Now when I get V as minus 30 centimeters, what does that mean? What does that mean? Where is the image formed? The image is formed somewhere here. So somewhere on the negative side. So somewhere here. So this is where the image is formed, which means the image is real or virtual. Think about it. The object's rays are not meeting at this point. Rather, probably they might be diverging. Probably they are, diverging or something like that. So probably you have to extend it behind so that they meet over here. You have to probably extend it behind so that they meet over here. That means it is a virtual image. What kind of image is it? It is a virtual image. As simple as that. Exactly. Okay. Kavin Santosh, I'll help you in a bit. Just let me complete this question. Just hold on. Now, if at all, I know it is not asked, but if at all a question was like, find the magnification, how much is the magnification? I know they have not asked it, but let's say they had asked it. What will you do? Let's use our formula. V by 𝛎2 divided by U by 𝛎1. What is image distance? It is minus 30. You have to substitute it with the sign. What is 𝛎2? 𝛎2 is basically 1.5. Whole thing divided by object distance is negative 15 divided by 𝛎1. 𝛎1 is nothing but 1 over here. Minus minus will cancel. So it will become 30 divided by 15 and this 1.5 will come over here. That 1 will go on the top. Okay. Perfect. 30 by 1.5, sorry, 30 by 15 is nothing but 2. 1.5 is nothing but 3 by 2. So the answer will be 4 by 3. Exactly. Now, because the magnification is positive, minus minus just cancelled out, that means the image is erect. The image is basically erect. If it was negative, then the answer will be, it is inverted. Right now, the answer is positive. Next important thing, 4 by 3 is more than 1 magnitude wise. Hence, the image is also magnified. The image is also magnified or basically enlarged. It is not diminished. It is enlarged, magnified, erect, virtual. Perfect. This is the complete nature of the image. Exactly. Cool. So let's move on to the next question. Yes, this is exactly what we are expecting. We have to solve this. But before this, let me just show you how you can find magnetism. Just go over here on our, see, this is our channel page, right? On the website, it will be easy. On tablet or on the mobile, this option does not come. Not this search. This search is completely different. I'm saying this search inside the channel. Just search over here magnetism, because when you search over here, na, it shows other channels and it might not even show this channels links, etc. Just search for magnetism. Just press search. Yep, you can see Pathfinder, magnetic sources and effects. Entire magnetism playlist is there. Okay, this. Okay, so this is our main playlist. See this full playlist. Exactly, this is the entire chapter. Bar magnets and Earth's magnetism, magnetic properties and materials. Some quiz is also there. This is not that chapter. This is completely different chapter, but it is in the complete magnetism playlist. Okay, so these are the two lectures which you will have to see: bar magnet, Earth's magnetism, magnetic properties and material. Cool. Okay, great. Shall we go ahead to the next question coming up on your screen? Okay, what does it say? It says, find the focal length of the glass sphere of radius r and refractive index 1.5. Wow, find focal length of a glass sphere. Interesting. So let's first draw a glass sphere and see what is exactly happening in that. So this is our glass sphere. Let us draw the principal axis like this. Okay. Now, rays of light will fall onto it parallelly like this. This is a parallel beam of light. Let me just get it. I want to find, oops, if a parallel beam of light comes like this, it will get refracted here and here. Eventually, it might meet somewhere. Just saying, okay, maybe it goes like this, refracts maybe like this, and maybe again refracts somewhere over here. Something like this. So this is where this point is exactly the focal point. This will be the center of that sphere. This is a parallel beam of light. In order to find the focal length, always what you need is a parallel beam of light, and see where does it converge. You can find where the focal point is. You can find where the focal point is. So let's try to figure this out. It's a very interesting question. So let's do it part by part, my dear students. Let's do it part by part. Let's understand what is exactly happening in this problem, and you'll understand why I'm saying part by part. The reason why I'm saying part by part is because this ray or this beam is getting refracted twice. And do you see, at this part there is a curved surface, at this part also there is a curved surface. So I will have to use the curved surface refraction formula 2 times. I'll have to use the curved surface refraction formula 2 times. Thank you, Usha. I'm so glad that you have started your preparation. Continue that preparation and let not that motivation die. Okay, so let's take each refraction separately and see what exactly is happening. First time, this ray will come like this and it will bend somewhere and go there. So obviously, this is our incident. This is our incident light. Naturally, this whole thing will become positive direction. Naturally, this whole thing will become negative direction, because remember, this will become our pole. This will become our pole. Our center of curvature is over here and it is at a distance of r. Okay, let's use our curved surface refraction formula. What does it say? Mu2 by V minus mu1 by U is equal to mu2 minus mu1 divided by r. Mu2, where is the refracted ray? This is incident. Refracted ray goes here. What is the material? Oh, it has a refractive index of 1.5. It's just clearly given. This is 1.5. So this is nothing but 1.5 over here. Perfect. So this is 1.5. What is V? I don't know. Mu1. Incident ray is present in air. So refractive index is 1. Object distance. Guys, where is the object? Very far, infinitely far. So negative infinity. Do you understand why negative infinity? It is a parallel beam. Rays are coming from infinity. Object is at infinity. So that's why minus infinity. Very good. So now what is mu2 minus mu1? Same order, 1.5 minus 1. Whatever order you wrote here, same order, 1.5 minus 1. Radius, it is r, but it is on the positive side because c is on the positive side. So it will be plus r. 1 by any infinity will be 0. So this part is just a big fat 0. Only this part is going to come. What is 1.5? It is 3 by 2. This has just become 0. What is 1.5 minus 1? It is 0.5. 0.5 is half. So this will be nothing but half and r will come over here. 2 cancels. So 3 by v is equal to 1 by r. Therefore, v is equal to just nothing but r divided by 3. V is nothing but r divided by 3. Everybody till this point, are they clear? Are you guys clear? Everyone? Cool. Shall we go ahead now? Till this point, if you are clear. Now, V is R by 3. R by 3, that means somewhere here, guys. R by 3 means somewhere over here. So, this clearly tells me that this particular ray is passing from here, something like this. I'm just showing this like this. And from here to here is basically R by 3. It is positive. It is positive. So that is why the image is formed over here. This is after first refraction. What will this image behave like? This image will behave like the object for the next refraction. Exactly. This image, which is formed over here, will now behave like the object for the next refraction. So this will be O2. This will be our center of curvature, of course. But now our pole has shifted. This is our pole. And because the rays were going like this, so that side will be positive. Be careful. Now this is our positive side. And this whole thing is on the negative side. This whole thing is on the negative side. We just figured out that from this side to this side, this is r by 3. So if I ask you, how much is I1C? How much is I1 to C? I1 to C is r minus r by 3. It is r minus r by 3, which is basically 2r by 3. So if from the center, this image is at a distance of 2r by 3, if it is at a distance of 2r by 3, so how much will this entire distance be from this particular pole? It will be nothing but 2r by 3, because this is 2r by 3, plus how much is this? How much is this? This is basically r only, right? So hence I will just put plus r. That's all. So how much is 2r plus r by 3? It is nothing but 5r by 3. That is the distance from our new pole. From our new pole. From our new pole, it is at a distance of 5r by 3. Got it? Very nice. Now let's again write our refractive, curved surface refraction formula. Outside is air. Air means refractive index is 1. So it is mu2 by v minus mu1 by u is equal to mu2 minus mu1 divided by r. What is mu2? Let's think. The rays from the object are going like this into this medium. This medium is air. Refractive index of air should be considered, which is basically 1. Which is basically 1, where the refracted rays. Image distance, do not know. Mu1, where is the incident ray? It is in the glass medium, which has a refractive index of 1.5. Object distance, it is at 5r by 3, but on the negative side, so minus 5r by 3. Mu2 minus mu1 is 1 minus 1.5. R is this time negative because you can see center is on the negative side. So this is minus r. Okay, so some bit of calculation is involved here. Let's do that. Minus minus becomes plus. 1.5 is basically 3 by 2. Okay, 5r is as it is. This 3 goes on the top. 5r is as it is. 1 minus 1.5 is negative 0.5, which is negative half. and this negative r is also there. Negative negative will become positive in the next step. Therefore, 1 by v will be equal to, this is 1 by 2r, minus minus has cancelled. Positive becomes negative on the other side. 3 3s are 9. 3 3s are 9. This will just become 10r. This will just become 10r. So, what is this going to be? 1 by v is equal to, LCM is basically 10r, my dear students. So, 2 goes with 10. How many times? 5 times. So, 5 minus basically 9. 5 minus basically 9. Therefore, 1 by v will be, 5 minus 9 is basically 4, but with a 5 minus 9 is basically 4, but with a negative sign, right? So this will be minus 4 by 10, which is minus 2 by 5. Oh, I forgot the r over here. So therefore, our v will be minus 5r, minus 5r divided by 2. What is this minus sign telling you? What is this minus sign telling you? Come on. What is this minus sign telling you? What is this minus sign telling you? Where is the image formed? Where is the image formed? Come on, my dear students. Yes, it is formed on the negative side. Exactly. So it is formed here. This is where our second image is formed, somewhere here. That means the ray goes somewhat like this, and you will have to extend it backwards. You will have to extend it backwards to figure out where the image is. Oh, interesting. So, yes, we'll have to extend it basically backwards right over here. Amazing. Yeah, it is inside the sphere. So basically, the rays are not converging. The rays are not actually converging. Rather, they are diverging when they pass through the glass sphere. So we thought earlier, where did it go? We thought earlier that the rays might converge, but it didn't happen, because this is obviously, you cannot know whether they're converge or diverge unless and until you actually solve the problem. So strictly speaking, the true diagram of this particular question would be, the true diagram of this particular question will be something like this. The rays, the rays go like this, the rays go like this, and then they even split more. The rays go like this, and then they split like this. You will have to extend them backwards to see where they meet, and this is where they meet. So this is our exact location of the focal point, and what you get is a divergent beam. What you get is basically a divergent beam. Perfect. This is what the diagram should look like after we solve the problem. Before solving the problem, we will never be able to guess this. But that's not the end story. Whatever distance you have measured is from point P, not from the center. So if I want to measure, from the center, one small change what I have to do is basically, see, from the pole, this distance is 5r by 2. This distance is 5r by 2, which is nothing but 2.5r. 2.5r is basically, somewhere here. 2.5r is basically somewhere, in fact, much behind this also. It is much behind this also. So if you measure it from the center, you have to subtract r from it. So if I want to measure from the center, the distance will be 2.5 r minus r, which is basically 1.5 r. 1.5 r. So this is the distance from the center. This is the distance from the center. So strictly speaking, even this diagram is not even so accurate, because this focal point is actually coming even here. This focal point is even coming much behind than what we expected. So in fact, that also I'll have to correct. And probably write it down like this. I'll probably start with this diagram here like this. probably show like this and then like this. So this would be the correct diagram. This would be the correct diagram. This is what is basically happening. You know? So it's basically going somewhere behind. Understood, guys? It's basically I'll have to go somewhere behind. I'll have to go basically somewhere behind. So this is exactly what is happening. This is where our focal point is turning out to be. Clear, everyone? Awesome. So these are the kind of questions which you can expect from curved surface refraction. This was a very good question, by the way. 3r by 2. Yeah, 3r by 2 is the correct answer, which is 1.5r, but that is from the center. Now, this actually leads us to something called as lens. What is a lens? Lens is nothing but two curved surfaces at the end of the day. Lens is nothing but two curved surfaces, just one after the other. Just imagine if I draw something like this. If I take a parallel beam of light like this, it will get refracted here, again refracted here, and probably it passes through this point. So probably all these rays meet over here, they are converging at this point. Perfect. This is nothing but a lens which is 2 times curved surface refraction. This is a convex lens because it is bulging out. Same thing applies to even concave lenses. Same thing also applies to even concave lenses. Maybe the rays which come here, they bend like this and they bend like that. Maybe I'll have to extend it behind here. Okay, so the rays come like this, go like that, and go like this. So they meet over here. So they are diverging. In this case, it's a concave lens. You can also have a lens which is like this, just one flat surface and one curved surface, which are called as plano-concave or convex lenses, where again you can have a ray which goes like this, gets refracted here, and then probably gets refracted here. Rays which go like this, and get refracted here, they are all meeting over here, they are converging. This is plano-convex lens. Similarly, this can go like this, and like this. You might have to extend it behind. Okay, might have to extend it behind. This is a plano-concave lens. So all these lenses are nothing but refraction for curved surface 2 times. So lens at the end of the day, a lens at the end of the day is nothing but curved surface refraction, curved surface refraction multiplied by 2 times. That's all. But you know what? We are going to do one interesting thing for lenses, which is there in our JEE. Compare it with this problem. This is also like a lens only with 2 curved surfaces. We have applied curved surface refraction formula once for this and once for this surface. Here, when we did this problem, one big catch was I have to shift the pole and I have to consider that extra distances which have to be calculated by simple geometry, because once the distances are calculated from this pole, so I have to go to the other pole, so I have to shift the pole and accordingly adjust the distances, which we have done here, etc. Just imagine this, if I tell you, hey, listen, whatever lens I am going to use, right, those lenses are going to be extremely thin. Those lenses are going to be extremely thin. So what happens because of that? Whatever poles will be there, this pole, P1, P2, and the optical center of this entire lens, which I will call it O, all these points will be very close. Think about it. All the points will be very close. So for a thin lens, pole 1, optical center, pole 2 are very close, which also means if there is an object which is placed here, maybe the image is formed here, whether you measure the object distance from point O or from P1 or from P2, it's roughly the same. Whether you measure it from P1, O or P2, it is the same. So therefore, the object and image distances, whether measured from, whether they are measured from pole 1 or optical center or P2, are almost the same, are almost going to be the same, which is very, very important. And usually we measure it from O, not from P1 nor from P2. ABCD not now, maybe sometime later, not now. Okay, at least after lenses, not before that. We'll do lenses combination only after that. So this is one very important assumption. And the last assumption which we'll be doing is this one. All the rays which we consider, they are always going to be close to the principal axis. Okay, so these rays are called as basically paraxial rays. They are called as paraxial rays. Their angles are very small, they are close to the principal axis. But if I have a ray something like this, which is going somewhere here, or let's say somewhere here, they are called as non-paraxial rays. They are called as non-paraxial rays. And we do not consider such rays. The only thing which we consider is only paraxial rays only. Keep this in mind. So these are certain assumptions which you should be aware of. Object distance, image distances are measured either from this, this or this, one and the same thing. Lenses are over here are thin, okay, and the rays which we consider are paraxial rays. Last thing over here before we go ahead, for a lens, you have two centers of curvature. Observe this carefully. Whether I take this lens over here or this lens over here or this lens over here or this lens over here, there are two centers of curvature. Observe carefully, guys. Now, if the light is coming from here, assume that our light which is there, our light is coming from this side. Our light is coming from this side. Light is coming from this side. Light is coming from this side. So this side becomes positive, this side becomes negative. So the first surface which the light hits is this one. Hence, this will be the center of curvature 1. And this surface gets affected later on because the light will first enter here, then go here. So that's why if you draw a big sphere, the center will be somewhere here. So this would be C2. Do you understand why this is not C1, this is not C2? Why this is C1, why this is C2? Okay, very, very important. Depends on where does the light hit first. When the light comes from here, it hits this surface first. This surface is part of a big sphere here whose center will be somewhere here. So now this will be C1 and this surface will get affected later on. The center will be somewhere here. So this will be basically C2. Same way for a plano-convex, this is a flat surface. Flat surface is a part of a big sphere whose radius is infinity. So center of curvature 1 is actually at infinity. You can't show it on this side or that side. Same thing is even applicable over here. The ray of light hits this surface, which is flat, which is like an infinitely large sphere. So center of curvature 1 again is basically infinity. It is at infinity. It's not existing. It's a flat surface. Now this is the second surface. The second surface is a part of this sphere here whose center could be somewhere here. So hence this is probably where our C2 will be. In this case, this is our second surface. Center of curvature will be somewhere here. So this is where our C2 will be. Now if I ask you what is the sign convention for R1, R2, etc. for all these cases. So what is R1 over here? What is R2 over here? What is R1 over here? What is R2 over here? What is R1 over here? What is R2 over here? What is R1 here and R2 here? Sign convention should be proper, guys. You cannot mess it up. Remember, this is our positive side. This is our positive side. This is our positive side because light is going like that. So this is our positive side. So think about it carefully. C1 is on the positive side, so R1 will be positive, R2 won't be. C2 is on the positive side, so R2 will be positive. C2 is on the positive side, so R2 will be positive. Here, nothing is on the positive side. For negativeness, always look like this. This is negative side. This is negative side, right? This is negative side. This is negative side. Clearly, C2 is on the negative side, so R2 is negative. Here, R1 is going to be negative. Yeah. Here, R1, R2 is definitely negative. What about R1? R1 is infinity, guys. I mean, C1 is at infinity, so radius of curvature is infinity. So this is basically infinity. That's how you get the sign convention for radius of curvature. Is this clear? All the cases I have taken. Plano concave, plano convex, convex, concave, everything. Is that absolutely clear, everyone? For the test portion, just go to the test tab and you will be able to see the portions also in it automatically. You will be able to see the portions also in it automatically. Now, what's the formula for the focal length? What's the formula for the focal length? Guys, if these lenses and the lens material is mu, if I know that the rays of light finally meets here, these are parallel beam of light which finally meets here, the focal length formula, which is called as the lens maker's formula or lens maker formula, is as follows. 1 by f, which is also the power of the lens, is given by refractive index of the lens with respect to the outside medium. So that is the relative refractive index, minus 1 into 1 by R1 minus 1 by R2. This P stands for the power. This is the power of the lens, and the SI unit of power is basically diopters. It is basically diopters. Power, if it is positive, then that means it is a converging lens or it is converging in nature. And if the power is negative, that means it is a diverging lens or diverging mirror. So that is what the positiveness or the negativeness tells me. And if the magnitude of the power is more, if it is more, then it means it has, that means it has greater convergence or divergence. If I tell you there is a lens whose power is 5 diopters versus 10 diopters, 10 diopters will converge faster as compared to 5 diopters. 5 diopters will take a long time to converge, 10 diopters will converge immediately. 20 diopters even more. If it is negative 10 diopters, that means the rays are diverging. If it is positive 10 diopters, it is converging. That is what the power signifies. F is the focal length measured from the center. This is relative refractive index. Don't get confused over here. This mu Lm, remember refractive index 1, 2 is nothing but mu 2 by mu 1. So this is mu L divided by mu M. This is for the lens medium. This is whatever is there outside. This is whatever is there outside. This is called as your lens maker formula. This is called as your lens maker formula. Cool. Let's use this lens maker formula to find out the power or the focal length of certain lenses. Let's do this. Biconvex lens, radius of curvature 20. Each refractive index of the material of the lens is 1.5. What is the focal length? Okay, fine, no problems. So let's draw the let's draw the lens first. It is something like this. Okay, has radius of 20 each. So that is, this is C1, and basically this is your C2, and this is on the positive side if the rays are coming like this, and obviously this is on the negative side. Okay, fair enough. Let's apply our lens maker formula. 1 by focal length is mu minus 1, 1 by r1 minus 1 by r2. So let's see what happens. Mu is directly given, outside medium is air, so it is nothing but 1.5 minus 1. What is r1? r1 is this. This is r1 and it is on the positive side, so it will be plus 20 minus r2. r2 is this. This is r2. It is on the negative side, so it will be minus 20. Okay, so 1.5 minus 1 is basically 0.5 multiplied by 1 by 20 plus 1 by 20 is 2 times of 1 by 20. 2 into 0.5 is 1, so it will be 1 by 20. So therefore, focal length will be 20 centimeters. Remember, this was 1 by f, so f will be 20 centimeters. It is positive, so it is on the other side. The focal length is on the other side. Perfect. Now, if somebody asks you what is the power of the lens, then you will just do 1 by f, but be careful. A lot of people will put 1 by 20. No, this is centimeters. So always put focal length in meters. This is SI unit. Power is measured in diopters in SI unit. So 1 by 0.2, guys, that is basically 5 diopters. So therefore, the power is 5 diopters. Focal length is 20 centimeters. Now what I will do, I'm just going to play around with this problem a lot so that you see how things can change. Accordingly. Now what I will do, I will immerse this in a liquid whose refractive index is 2. I will immerse this in a liquid. This liquid has a refractive index of, very high refractive index of 2. So what will happen to the focal length inside the liquid? Inside that particular liquid. I have just changed that question. Let's find out what is going to happen. Okay. Again, use lens maker formula. 1 by f is equal to, remember, this is relative refractive index, 1 by r1 minus 1 by r2. Okay. Now this mu is lens's refractive index with respect to the medium. Remember, this was mu L divided by mu M. 1 mu 2 is mu 2 by mu 1. What is the lens refractive index? It is 1.5. What is the refractive index of the medium? It is 2. Okay. 1 by r1. r1 is on this side, the positive side, so plus 20. r2 is on the negative side, so minus 20. Okay, let's see. 1.5 is 3 by 2. So 2 2s are 4. So 3 by 4 minus 1. This will become 2 times of 1 by 20. 3 by 4 minus 1 is nothing but minus 1 by 4. And into 2 by 20. 2 goes with 4 2 times. So it will become basically 1 by, with negative sign, 40. This is 1 by f. Therefore, f will become minus 40 centimeters. Interesting. Now, the best part is about the power. Power being 1 by f, which will be 1 by minus 0.4. What is 0.4, guys? It is 4 by 10 over here. So that power, which will become now 5 by 2, which is minus 2.5 diopters. Interesting. It has now become negative 2.5 diopters, which means this lens, which was right now converging, has now become a diverging lens. And that is possible if you immerse a lens in a refractive index which is higher than the lens's refractive index. So you can change not just the focal length by changing the outside medium, but you can also make a converging lens diverging and a diverging lens converging. Usually, our concave mirror, reflecting mirror, they do not get affected by the medium. The focal length of a mirror is r by 2. Whether you put water, diamond, glass, doesn't matter. A concave mirror will always be converging. A convex mirror will always be diverging. But a convex lens may be diverging, may be converging, depending on the outside medium. Same way, a concave lens may also be diverging or converging depending on the outside medium. Is that absolutely clear? Very, very crucial information. You can also solve a problem for plano concave just for the sake of it. Imagine this has a refractive index of 4/3 and this has a radius of curvature of, let's say, 30 centimeters. We have to find what is the focal length. Question is find focal length and power. Let's use our formula. Simple. So 1 by f is equal to mu minus 1 into 1 by r1 minus 1 by r2. What is refractive index? Well, it is 4/3 minus 1. 1 by r1 minus 1 by r2. This is the first surface. It's a flat surface. So the radius of curvature will be infinity. The second surface is the curved surface. The center is going to be here. Remember, C1 will be at infinity because it is a flat surface. C2 is here on the positive side. So it is going to be plus 30. Perfect. So what will this become? 4/3 minus 1 is nothing but 1/3 into 1 by infinity is 0 minus 1/30. So that is 1 by f. So therefore, f will be 330 will become 90. So minus 90 centimeters. Minus 90 centimeters. Yep. That's why it is hard to see with specs in deep water. Correct. Very good. You finally understood what is the working principle. And if you wanted to find the power, power was 1 by f. So it is 1 by minus 0.9, which is minus 9 over here and 10 over here. That's it. You can just put the power as minus 10 by 9 diopters. Diopters. That is the answer. What an amazing question, right? So this is how you solve plano concave or plano convex questions, where one of the radius of curvature will be infinity. 1 by infinity is 0. Okay, fair enough. Let's go ahead. Okay, just put the question here. Let me just put it here. Now let's talk about magnification, velocity of image, all these things for a lens. For a lens, let me just create a duplicate. Now imagine you have placed an object here. This is your object distance. The rays go like this, like this, and maybe finally they meet somewhere over here. This is where our image is. So this is our image distance. So the lens formula, just like you had the mirror formula, you have the lens formula. 1 by v, 1 by u is 1 by f, but there is no plus sign here, there is minus sign. That's the only difference. 1 by v minus 1 by u is equal to 1 by f. That's the only difference. The sign will change, rest all formulas, etc. Everything will remain the same. Everything will remain the same. Okay, keep this in mind. Okay, so what about the other formulas for magnification, etc.? All the formulas are the same except for the signs. For example, when we talk about height-wise magnification, which is height of the image by height of the object. Meaning, imagine this is our object, and let's say this is our image, this is our object, this is our image. This object will have some height HO, it will have some height HI. This magnification which happens perpendicular to the principal axis. Where is it happening? Perpendicular to the principal axis. Very, very important. Perpendicular to the principal axis. That is called as your lateral magnification. I had explained this in mirrors also. That is just V by U. There is no negative V by U. What is it? Just V by U. There is no minus sign. That is called lateral. Lateral is perpendicular to the principal axis. V by U. Okay. Now, the other kind of magnification that you will get is along the principal axis, which is along. So length of the object is like this. It might widen up or become thin. I'm standing in front of a lens. Yeah, I might become tall, but my body width might also become thin, or it might expand, okay, along the principal axis. This is length of the image. So you have the magnification like this, which is called longitudinal. This will be length of image by length of object, which will be V by U the whole square. As simple as that. Same formula. This is nothing but V by U whole square. Is that clear? Everyone, till this point? Lastly, velocity of image and velocity of object, guys. Very straightforward formula. Very, very straightforward formula. So, guys, you have any kind of lens, doesn't matter. Let's say this is our object. Let's say this is our image. Our object and image, they have some velocity. This is velocity of image. This is velocity of object. If you want to find velocity of image and you know velocity of object, all you have to do is just know the longitudinal magnification. That's it. The same formula is applicable here. So whatever is the longitudinal magnification formula, V by U the whole square. That's it. That will give you the velocity of the image with respect to the object. Cool. Shall we go ahead? Let's do some questions. Because sign convention is same, formulas are similar, there is nothing new, okay, except for the lens maker formula, which you have learnt now. Okay, so let's go to the questions coming up on your screen. There is an object of length 2 centimeters is perpendicular to the principal axis of a convex lens. Focal length already given. Find the size of the image if the object is at a distance of 8 centimeters from the lens. Level 1 question, just to get you started, just to get you kick-started. Let's do this particular question, my dear students. Come on. I think you two can start solving it very easily without even waiting for me. How do you do this? Yep. Object's length is given. I know focal length, I know the object distance. So I have to start with 1 by V minus 1 by U is 1 by F. We all know our lens is going to be like this. Our object is somewhere going to be here. This is going to be the positive side. This is going to be the negative side. Correct? So, and the focal point will be somewhere here. So this is our focal length, because converging lens, it will converge on that side. Okay, so let's see, 1 by V. What is image distance? What is image distance? I don't know. What is object distance? It is going to be, where is it? 8 centimeters, but with negative sign. What is focal length? Focal length is plus 12. That's it. Therefore, 1 by V will be 1 by 12. Minus minus is plus. On the other side will again become minus. Well, you can take the LCM, obviously. 12 and 8, guys. 12 fours are 48 and 8 6 are also 48. You can just take that, right? Very good. So take this as 48. This goes with this 4 times. This goes with this 6 times. So it will be minus 2 by 48, which is minus 1 by 24. Therefore, V will be negative 24 centimeters. This means the image is on this side only, minus 24, somewhere here. This is where the image is. That means it is not any image, it is a virtual image. What kind of image is it? It is nothing but a virtual image. Everyone, till this point clear? All right. Next, what about the magnification? If you just try to find the magnification, I know they have not asked it. Oh, they have asked, find the size. So it will be nothing but V by U. So magnification is height of the image by height of the object. V is how much minus 24, u is how much? Minus 8. So it will be minus minus cancels, plus 3. It is plus, that means it is erect for sure. It is more than 1, that means it is enlarged. It is definitely enlarged for sure. But this is height of image by height of object. What is the height of object? It is basically 2. So this is basically 3. So height of image is 3 to the 6 centimeters. So it is basically 6 centimeters. Everyone? Mayank, which mock test, my dear? Which mock test are you talking about? Okay, cool. 6 centimeters. Perfect. Moving on to the next one. This is level 2 Tatva question. Let's see what is this particular question. It has slightly more data. So I think it will be probably little bit lengthy maybe. Okay. So let's do this particular question. Okay. Get ready, guys. NLM will come up after some 1-2 weeks, because next week I'm doing relative motion. Then I'll also do capacitors and current electricity. And then I will go to Newton's laws of motion. So it will take a couple of weeks, 2 weeks at least. Okay. Okay. Let's do this. A double convex lens glass refractive index 1.6 has both surface of equal radii of curvature 30-30. Object of height, this is placed here. Calculate the size of the image formed. So a lot of things are there over here. It's a double convex lens. It's a double convex lens. So this is where center 1 will be. This is where our center 2 will be if the light is coming from this side. This is the positive side and this is the negative side. Okay. So first of all, the focal length, which is mu minus 1, 1 by R1 minus 1 by R2. So mu, what is the refractive index? 1.6 minus 1. Radius 1 is positive. How much is the radius of curvature? 30. So 1 by 30 minus, this will be minus 30 because C2 will be on the negative side. So this will be 0.6 multiplied by minus minus is plus. So 2 times of 30. So 6 goes with 35 times. So this will be 50 times. So this will be 2 by 50, which is 1 by 25. That is 1 by f. Therefore, f will be 25 centimeters. F will be 25 centimeters. Everyone? Now, what is the next step? Okay, our lens is given. Focal length is known. Object is placed. Where is the object placed? 12.5. Our object is placed here on the negative side. This is the positive side. You have to find where the image is formed. Use 1 by v minus 1 by u is equal to 1 by f. Object distance is negative 12.5. It is on the negative side. Focal length we just figured out to be 25. It will be positive. Okay, 1 by v will be 1 by 25. Minus minus is plus. On the other side again becomes minus. Now 12.5 is actually 25 by 2. 25 by 2. Okay. So this will just become 1 minus 2 is minus 1 by 25. Therefore, v will become reciprocal of it, which is minus 25 centimeters. Minus means somewhere here. So the image is formed somewhere here only. So it is definitely virtual in nature. Lastly, what do we have to figure out? The size of the image formed. So height of the image by height of the object is just v by u. Height of the image on height of the object is 5. V minus 25. Object distance minus 12.5. Minus minus cancels. 25 by 12.5 is 2. So height of the image is 5 into 2. So that is basically 10 centimeters. Since this was positive, hence it is erect, and since it is more than the object size, it is also enlarged. It is also enlarged. Is that clear, everyone? Everyone clear about this? Perfect. So sometimes you might get some lengthy questions also like this. You might get some lengthy questions also like this, where everything has to be calculated. Why do we have a blank slide? We don't need it. Yes, it is. Wow. Next question coming up on your screen. What do we have? There is a beam of light which converges to a point P. A lens is placed in the path of the convergent beam 12 centimeters from P. Okay. At what point does the beam converge if the lens is convex lens of focal length concave lens or focal length. Okay, we'll take two cases, so we'll take two slides. First, let's do this particular part. This part. Convex lens of focal length 20. Beam of light converges at point P. See, understand what this question means. You have a convex lens. If that convex lens was not there, ideally, that beam would have continued to go and meet at some point P. But because of the lens, it gets deflected and it will meet over here. So that point P now is actually an object which is virtual because the rays wanted to meet there. So that point P is actually a point of virtual object because the rays wanted to meet there, but they didn't actually meet there. Where it actually meets is over here, and that is where your real image was formed. That is where your real image is formed. Okay, so I want to find what is that point. Let's use lens formula. 1 by V minus 1 by U is 1 by F. I don't know V, I know U. The rays are going like this. The rays are going like this. So this should be the positive side. This should be the negative side. Object distance is not negative, it is positive. It is plus 12. Focal length is 20. Oh, got it, guys. So this will go on the other side. This will be 20. This will be minus will become plus. The LCM is 120, let's say. So 20 goes with this 6 times. This will go with this 10 times. So this will be 16 by 120. You can divide it by 4. This will become 4. You can divide it by 4. This will become 30. This will become 2 by 15. Therefore, V will become 15 by 2, which is 7.5 centimeters. So instead of converging 12 centimeters, now it will converge at 7.5 centimeters. That is what it means. Mayank Khatri, how do I know your school foundation mock test syllabus? How would I know? Okay. Now, what about this? Concave lens of focal length 16 centimeters. Okay, no issues. We'll try to solve this also. It's not that difficult. Imagine this same lens was concave. The rays wanted to meet over here. The rays wanted to meet over here. This is the point of your virtual object at that point. But because of the diverging nature, they might probably end up going like this. They might end up probably going like this. And now they might meet somewhere over here. So the image will be formed somewhere else. I don't know where they are diverging, where they are converging or not. So I will better solve it by the lens formula. 1 by V minus 1 by U is equal to 1 by F. Therefore, 1 by V, I don't know, U is positive. How much? Concave length of some other focal length, but distance is still 12. Focal length for concave will be negative. Focal point is here. Do not forget. So this is minus 16. Everybody understood why negative? Because it is on the other side. Because it is on the other side. Correct. Come on, solve this now and tell me how much are you getting. Solve this now and tell me how much are you getting. So this will become positive minus on the other side by 1 by 16. So LCM is 48. This goes with this 4 times, this 3 times, 4 minus 1 is 3. Sorry, 4 minus 3 is 1. So V will be just 48 centimeters. Okay, so it is coming out to be positive. That means the rays are diverging slightly away and they are meeting somewhere over here. This is where the image is formed. Okay, and it is converging at this point. So it is a real image. So a real image is formed. So real image is formed at a distance of 48 centimeters. What a question. What a question. Loved it. Shall we go ahead? Shall we go ahead, guys? Okay, let's go. 48 and 7.5. Perfect. Moving on. Now we have come to combination of lenses and silvering of lenses. So we'll see some combined questions before going to optical instruments, which will be the last part. Thank you, Nish FX. Thank you so much. Let's see combination of lenses. Whenever you have a lens like this, along with another lens like this, maybe some another lens like this, that is basically combination of lenses. And in optics, there is a golden rule when you have multiple things happening one after the other. Just like when you pass from the second standard, you are probably the entry students for the third standard. When you pass out of third standard, you are by chance. This lens, you are considering there is an object here. This object may form an image over here. Who knows? After the first lens, this image now becomes the object for the second lens. Maybe the image is formed, I don't know, just here, just taking some random case. Let's say this is the image formed by the second lens. This image is now the object for the third lens. Maybe the image is formed somewhere here. That is how you locate the image. So the logic is, my dear students, the logic is the image by a lens or a mirror is the object for the next. This is the main thing which you should remember. So you may have to use lens or mirror formulas multiple times. While doing so, a word of caution. What is that caution? Keep in mind that when you do so, the image distance I1 will be measured from this lens, but that won't be the object distance because this object is for the next lens, so you will change the pole. The image from this will be the object for the next, so the pole will change, the distances will be changed. So you have to shift the pole, number one. Number two, the sign convention might change. Maybe the ray is going like this, it reflects and comes back. So the sign convention could change. So the caution is, the image or the object distances may change, or rather will change with next lens or mirror for the new poles which are there. Not just that, and the sign convention as well, and the sign convention as well. So guys, keep all these things in mind. The sign convention will also change, and probably even the image distance, object distances could also change. So you have to keep this in mind when you solve multiple lenses and mirrors as a combination. But there is a sweet spot over here. And the sweet spot is when the lenses are together, touching each other, and they are thin. So this is where you have a special criteria, of thin lenses in contact. When you have that, only then you can take the effective power as P1 plus P2 plus Pn, which means 1 by the effective focal length is 1 by F1 plus 1 by F2 plus 1 by Fn. That means all these multiple lenses which could be there, maybe you have a concave lens, maybe you have a convex lens, maybe you have again a concave lens, maybe you have plano-convex lens, all these things you can combine it as one single lens. You can have this as F1, F2, F3, Fn. This will be F effective. So you can combine them as one single thing only if they should be thin, because then the distances will change. As you put more lenses, the distances will change. So that is why they should be very thin and close, or else do not use it. That's why I put thin lenses in contact, both the criteria. If it is thick or it is not in contact, you have no other option but to use this method, which is quite lengthy. But it is to be done. There is no other option. Hello, Mesu. Clear till this point? Absolutely. Everyone? Okay. Chalo. Let's do some questions based out of this. Let's do some questions based out of this. And before we go ahead, here is the, yeah. Oh, very nice question we have. Too similar. This is one of the best questions. This is not even level 1. Actually, this can be level 2 also, or level 3 also. Two similar plano-convex lenses are combined together. Three different ways are shown. The ratio of the focal length of their combination is. First time, their flat surfaces are touching. Second time, the concave of one is touching the, convex of one is touching the flat. Last time, both their convex surfaces are touching. Very nice question. Okay. If you can answer this, I will be really, really proud of you. Just take a moment and solve this. Come on, everybody spam the answer in the chat box right away, right now. I'll tell you what is the logic, what is the hidden concept here. If you take plano-convex lens like this and try to find the focal length, it will be mu minus 1. First surface is infinity. Second surface has a negative radius of curvature, so minus r. So this will be mu minus 1. Minus minus will become plus, and it will become r. So 1 by f is this. So f is basically divided by mu minus 1. Next, let's say I turn it like this. Let's say I keep the flat surface here and this is the curved surface. Remember, light is coming from this side. For this scenario, the light was coming from here. What do you think will the new focal length be? Will it be negative of this 1 minus mu or something else? This is the best part, guys. So mu minus 1. First surface is here, center of curvature will be somewhere here, so it is positive. So 1 by r minus 1 by infinity. 1 by infinity is 0. So it will be mu minus 1 by r. So f will be again r by mu minus 1. What does this tell you? It is the same, no change in sign. So that means from these two, one can say that the which side comes first doesn't matter. Which side comes first doesn't matter. Very, very important, guys. A lot of people think this will become positive, this will become negative, but it is not. In fact, it is the same magnitude also and sign also. So now whether you hold the second lens like this or like this, like this or like this, like this or like this, how does it matter? They are thin lenses in contact. Each of the plano-convex lens has the same focal length. Whether you hold it like this or like this, it doesn't really matter. So you take this lens and you turn it like this, it doesn't really matter. So in fact, all of them should have the same focal length. All of them should have the same focal length. Hence, the answer is 1:1:1. What a tricky question, isn't it? So many people waste a lot of time, but if you know this trick, because I've taught you now, you can solve this within seconds. Moving on to the next question. Oops, by mistake answer is shown. Oh, okay. Okay, this was asked in JEE Mains 2022. One of the most important questions, guys. You break the lens in 3 different parts. What do you think is the power of each lens? Okay, so let me tell you, very simple thing. If you take a lens like this and you break it into 2 parts like this, guys, if this original lens had a power of P, focal length of F, each of this lens also has the same power, same focal length, same power, same focal length. Reason being, in this case, there were many rays which were going, and they were converging at a point. Many rays which are going and converging at a point. Now, if you take any one of them, you have exactly half the rays which are going. You have basically exactly half the rays which are going, but still they'll meet at the same point. So what reduces is the intensity. The intensity reduces, but where they intersect, That does not change. So focal length and power will not remain, will not be different. That's one thing. But if I split it up like this, things will be different. The power will get divided. So this will be P by 2, P by 2. Power is inversely proportional to focal length. So this will be 2F and this will be 2F. I've seen a lot of students doing this silly mistake. They say power will become half. Sorry, power will become double or something and focal length will become half. No, guys, the power gets divided. This is less powerful than the original lens. P by 2 plus P by 2 is P. How does the lens combine? I just showed you the formula right over here. What is the formula? P1 plus P2 plus P3 is the P effective. This is the formula. And focal length does not add. Reciprocal of the focal length adds. Oops. Where is it? So this is P by 2 and this is double the focal length. So hence what happens is when you divide it like this, if the original power was P, focal length was F, then this will still be P, this will be still F. This only intensity has reduced, that's all. But you're also breaking it like this. So this will be P by 2 and this will be 2F. This will be also P by 2, this will be 2F and 2F. There is only one option which matches over here, which is option number A. None of the options will match. Check it out. None of the other options will match. Power of lens L1 is P by 2, wrong. Power of lens L3 is P by 2. This should have been correct. I don't know why they have not marked it as correct. Power of lens 1 is P. Yes. So choose the incorrect options. Power of lens L1. It should have been option B, guys. I don't know why they marked it as option A. The incorrect one. The incorrect one. This should be the incorrect one. All the others are correct. This is correct. This is correct. This is correct. I think the answer mark there is wrong by mistake. Yeah. The incorrect one is question. Got it? Power of lens number 1 is not P by 2. Okay. So I'll delete that slide. That is wrong answer given over here. This is definitely wrong answer. Okay. Cool. Moving on to the next question on your screen, and here it is, JEE Mains 2024. Effective power of a combination of 5 lenses are 25 diopters, the focal length of each of the lenses. Very simple. 5 lenses are there, so 5 times each lens. 5 times each lens's power is basically 25 diopters. Therefore, the power of each lens is 5 diopters. Power is 1 by focal length. So focal length of each is basically 5. So F of each is basically 1 by 5 meters. But if I convert it into centimeters, I'll have to write 1 by 5 into 100 centimeters, which is then 20 centimeters, which is B for IIT Bombay. Yep, that is correct. B for IIT Bombay. Got it, everyone? Very good, Supreme Soul. Awesome. Can we use the formula and check for the focal length and then divide it into half? Yeah, you can do that, Nikhil, but it will be again lengthy. Why would you want to do it the lengthy way? Keep it simple. Now the last concept here before we go to optical instruments, okay, is the silvering of lens concept. Now there are two kinds of usual problems that you get in silvering of lens. One kind of problem is where you have a plano-convex lens and this side is silvered, it is made shining. If this happens, I mean, just go for it, guys. It's going to be one of the simplest problems because I'll tell you why. If this is a mirror, what does a mirror do? If you stand in front of the mirror, it replicates you. So Pavam, this mirror is just replicating you. Actually, what it is trying to do, actually my goodness, what it is trying to do is whatever is there in the front, it will replicate it behind. So just think of it as if this plano-convex lens will be replicated like this over here. Oh, so what has happened is a plano-convex lens has now become a double convex has become now a double convex lens. It becomes so simple. So guys, now if our object was here and the question was where will the image be formed, etc. So you now just look at this as the simple lens. Use, what will you use now after this? Use the lens formula. Use the lens formula. And finally, what will you do? Locate the image. You will basically locate the image. Now, this is the tricky part. Once, let's say you located the image here, lot of you will be like, the image is formed 10 centimeters, behind the mirror. So, a lot of you will be like, sir, the image is formed here. No, that is the wrong part. See, guys, I had opened this up. I had replicated this. So, again, you need to collapse it back. You need to collapse it back. So, what will happen is in our final diagram, in our final diagram with this thing over here, maybe the object is over here. You are going to see where the image is and you are going to bring it back. You're just going to bring it back. Maybe the image will be here. So that is how you're going to find the location of the image. Did you understand the process? Did you understand the process? When will I take kinematics? Kinematics is already taken. Charanjit, just over here, go back on our live section. It's there. You can check it out. I'm in fact starting 1D relative, 2D relative. Where is it? Motion in 2D, done. Motion in 1D part 2. Motion in 1D part 1. Detailed classes. All my classes are detailed if you notice. Okay. Yeah. So it's already done. I'll repeat. If you have a plane mirror and there is an object, imagine plane mirror is there and in front of it there is a convex. The convex lens is flat. The flat part is silvered. That means it is mirrored. Then what does a mirror do? It replicates whatever is there in the front. Correct? Okay. So there was a lens in the front. Think of another lens behind. Plano-convex. Two plano-convex lenses is like a double convex lens. Treat it like a simple double convex problem. Now use lens formula. 1 by v minus 1 by u is equal to 1 by f. You will find where the image is. Let's say the image comes at a distance of 5 centimeters. But actually, will the image be at a distance of 5? No, because you had opened this up. You had replicated. You close it back. And you close it back, it will be at a distance of minus 5. If the image comes at a distance of already minus 7, so then when you close it, that minus 7 will go here, it will become plus 7. That minus 7 will then become plus 7. Got it? Understood? Akka? All right. This is one kind of question which you can get. Another kind of question which you can get is where the curved surface is only silvered. Imagine something like this. If this happens, right, what you should do is treat it like a concave or convex lens and a mirror separately. These are two separate things. And keep in mind one simple thing. Whatever ray of light will come, enter and exit back, it will do the same thing here. But when it does, it first enters the lens, then enters the mirror, and then again enters the lens, and then again exits it. So you can see it enters the lens, hits the mirror, and again enters the lens. So lens is encountered how many times? 2 times. Mirror is encountered how many times? 1 time. Hence, this diagram of a silvered lens, especially when the curved surface, not the flat surface, is there, it is actually like two lenses and a mirror. Oh, two lenses and a mirror, is it? Eventually, the ray is coming back. See, if the ray passes, whether you take concave or convex lens, if the ray comes from here, it has to go on the other side. Whether virtual image is formed, real image is formed, the ray has to go on the other side. That's what a lens does. But whether you take a concave mirror or a convex mirror, the ray has to return back. Whether it is a real image or a virtual image, doesn't matter. Now, what has happened over here? Did the ray pass or did the ray come back? The answer is obviously it came back. Oh, so that means this whole thing together is actually a mirror. This whole thing together is going to be an effectively an mirror. It is an effective mirror. It is an effective mirror. It could be any kind of mirror, guys. I don't know, but it is definitely going to be a mirror. Maybe it is a more convex mirror. I don't know. I'm just saying. It's just going to be a mirror of a new focal length of a new, yes, power. So now what I will say is the power of the effective mirror is equal to power of the lens 2 times plus power of the mirror. That's all. That's all. Lens power formula is 1 by focal length of the lens. Power of the mirror formula is not it's not 1 by f, it is minus 1 by f. Remember, all formulas are same, just that the sign changes. So it will be negative 1 by f. And since it's a mirror, this will be also minus 1 by f effective. That's all. So this is the logic to find the effective power. This is the logic to find the effective power. Is that clear? Shall we see some questions based on this? Shall we see some questions? Actually, the questions that I have are different kind of questions. But first, let's see these kind of questions. Let's start with the easier one, where you have this thing. This is silvered. Okay. And I tell you, listen, this is 1.5. Listen, the radius of curvature is 20 centimeters. Okay, listen, the object is placed over here at a distance of, let's say, 50 centimeters or something. This is where your object is placed at a distance of 50 centimeters. The question is, where is the image formed? Image, where is it formed? Okay, so let's try to do this question. What did I tell you just some time back? Whenever the flat surface is silvered, whatever is there in the front, just replicate it behind. So what will it behave like? A double concave lens, correct? It will just behave like a double concave lens. So now this is 20, this is also 20. So I can find the focal length using our focal length formula, lens maker, 1 by r1 minus 1 by r2. This is your center 1, this is your center 2. So 1 by f is equal to mu is 1.5, oops, 1.5 minus 1. 1 by radius 1 is negative. This is negative side. This will be the positive side. Minus 50 minus plus 50. So 1.5 minus 1 is 0.5. Negative negative 2 times. So minus 2 times by 50. 2 into 0.5, 1. So minus 1 by 50 is 1 by f. So f will be minus 50 centimeters. Perfect. Now let's use our lens formula. Okay, so the object is over here. I want to know where is the object? 50 centimeters. Oh, why did we get 50? Sorry guys, sorry. Radius was not 50, my bad. It was 20, my bad. So it's minus 20, this was also plus 20. So this is 0.5 into minus 2 by 20. 2 into 0.5 is 1. So this will be minus 1 by 20. That's 1 by f. So f will be minus 20 centimeters. Okay. That is minus 20. Object is at a distance of 50 centimeters. So let's use our lens formula. 1 by v minus 1 by u is equal to 1 by f. So therefore 1 by v, I don't know. U is minus 50, negative side. 1 by f is minus 20. Therefore, 1 by v is equal to minus is plus, goes on the other side, becomes negative again. So minus is common. So 1 by 20 plus 1 by 50. LCM is 100. 20 goes with 100 5 times, 50 goes 2 times. So it will be minus 7 by 100. So that means v will be minus 100 by 7 centimeters. Now, what does this mean? V is minus 100 by 7 centimeters. That means the image is somewhere here. The image is somewhere over here, but for this lens. That is for this lens. So when you combine it back again, when you again, put it back in its, sorry, it was not like that. When you again combine it back like this, if this image came out to be negative, actually it is not here, it is over here. So the image will be formed over here at a distance of 100 by 7 centimeters behind the mirror. That means it is going to be virtual in nature. It is going to be virtual in nature. Got it, everyone? Clear? What a brilliant question. Yep. What a brilliant, brilliant question, isn't it? It is on that side. Similarly, I can give you one more question where you might have this thing silvered and maybe this is 20 centimeters, maybe this is 10 centimeters. And the question will be, what is the effective combination going to behave like? What is the effective combination going to behave like? Okay, fair enough. I know whenever I have a curved surface which is silvered, I have to go by this logic. I have to break it into two lenses and a mirror, and effectively at the end of the day, it will behave like a new mirror because the light rays will be reflected eventually. So I'll just think, okay, there is a lens here, there is another lens, sorry, there is a lens here, and then there is a mirror here. Okay, so two lenses and a mirror. So 2 times power of the lens plus the power of the mirror. Eventually, it will behave like a mirror. Eventually, it will behave like a mirror, which is called as our effective mirror. Okay, perfect. What is this power of this lens and power of this mirror? Okay, so let me just create a duplicate right now. What is the power of this convex lens? So for that power of the lens, which I have to do as 1 by FL, it will be mu minus 1, 1 by R1 minus 1 by R2. What is refractive index? Okay, I think that refractive index part was missing. Let's say this is basically having a refractive index of 2. Example. So this will become 2 minus 1. Okay, 2 minus 1. 1 by R1. What is R1? The first surface is on the positive side, so plus 10. This is C1 on the positive side. This is C2 on the negative side. Minus 1 by R2. R2 is negative 20. This 2 minus 1 is 1. Minus minus will become plus. So LCM is 20. So this will become 2 plus 1. So guys, that power of that lens is just 3 by 20. 3 by 20. I'll just leave it as it is. I'll just leave it as it is. What about the power of the mirror? For the power of the mirror, remember it is minus 1 by f. What is the focal length of the mirror? It is r by 2. What is the radius of curvature of that mirror? This mirror has a radius of 20 but negative. So minus 20 by 2, which is minus 10. So put that over here, minus 10. It will just become 1 by 10. So that is the power of the mirror. Minus minus became positive. Everybody getting this point? Why is it positive? Everybody understood this point? Okay, it's just easy. If you want me to conduct derivatives and integration, do let me know. I'll take a separate class for it later on. Okay, I'll just put that up. No issues. Okay, perfect. Now is the next part where I have to use these values. 2 times power of the lens. What is the power of the lens? 3 by 20. Let's put that over here. 3 by 20 plus power of the mirror. What is the power of the mirror? 1 by 10. It is nothing but 1 by 10 is equal to effective power of the mirror, which is minus 1 by f effective, because minus because it's a mirror, nothing else. Okay, let's solve this. 2 goes with 20 2 times, so this will be 3 by 10 plus 1 by 10. 3 plus 1 is 4 by 10, which is 2 by 5, is nothing but minus 1 by f effective. Therefore, the effective focal length is negative 5 by 2, or basically minus 2.5 centimeters. That is the answer. That is the answer. So this entire thing behaves like a negative focal length for a mirror means it's a concave mirror. So concave mirror of 2.5 centimeters magnitude focal length. That is what it behaves like. So we have solved this. This is how the questions are. Clear? Okay, let's solve some mixed questions also on ray optics. Look at this particular question, my dear students. In this particular diagram, the direct image is formed by the lens of an object placed at O and formed after reflection from the spherical mirror are formed at the same point. What is the radius of curvature of the mirror? Basically, the object and the image which is formed finally, they coincide. Okay, let's think what might be happening. Let's just think, okay? Just create a duplicate here. Probably the rays go like this, they go like this, they hit back, and they go like this. That is what should happen. Guys, but this can only happen in one peculiar scenario. This can happen in one peculiar scenario. I feel the rays should retrace back, then the image will be formed on the object. Think about it. If our image after reflection is formed on that particular object, that means the rays should retrace back. If the rays have to retrace at any point of time when there is a mirror, understand the rays are falling perpendicular on the mirror. And for a curved mirror, that happens only when the rays are passing through the center, because when you take a circle and you draw a line passing through the center, it is perpendicular to the circle, because that will be the radius. The radius is perpendicular to the circle's circumference. So, if the center of curvature of this particular lens, this is very, very crucial in this understanding of this particular problem. This is the center of curvature. On that center of curvature, those rays must be passing through it. So it should go probably like this. It falls on it perpendicularly. It falls on it perpendicularly like this. So if it goes like that, it also returns back like that. And it goes like this. This is exactly what is happening. It is retracing back the same path and falling over here. That means the image of this particular object, whatever we are considering, if this is our object, the image should be formed over here. Okay. Next, we have to find the radius. The focal length is given of the lens. Object is placed at O. The distance is given. Let's use lens formula. So 1 by V minus 1 by U is equal to 1 by F. What is V? I don't know. U is minus 15. Focal length 10, because it's convex lens. It's converging. This, I'll take it on the other side. Minus minus is plus. On the other side will become minus. 30 is the LCM. 10 goes with 33 times. 15 goes 2 times. 3 minus 2 is 1. But remember, this is 1 by V. So V is basically 30 centimeters. That means this is basically 30 centimeters. Now, if that is the center of curvature, that means this distance which is there will be the radius of curvature. How much will that radius of curvature be? 50 minus 30, which is 20 centimeters. So the radius of curvature of that mirror will be 20 centimeters. Yes, that is the answer. Understood? So this is a combination of lens and a mirror problem, but you have to use some logic, you have to use your brain, you have to use your creativity and simplify it as much as possible. You have to think, oh, it's formed at the same place. That means the rays are retracing back, right? What a brilliant, brilliant question, guys. Let's look at a JEE mains question, which is there before we head out for the break now. Okay, we'll meet again for the optical instruments part. The position of the image formed by the combination of the lenses is, where do you think the image is formed by the combination of these lenses? You just have to use lens formula multiple times. That's all, guys. Let's start it. First over here, this is our object. I will find the image using 1 by V minus 1 by U. U is minus 30 is equal to 1 by focal length. Focal length is 10. Excuse me. So 1 by V will be 1 by 10 minus 1 by 30. LCM is 30. 10 goes with 33 times minus 1, which is 2 by 30, which is basically 1 by 15. So V1, this is the first image, will be at a distance of 15 centimeters. So, okay, 15 centimeters. That means the rays from the object will try to meet somewhere over here. Now, this distance, I tell you, is 15 centimeters. This is where the first image will be formed. Interesting thing to note is the focal length of the concave lens is 10. See, out of 15, if you remove 5, how much will you get? If you out of 15, if you remove this 5 centimeters, how much will you get? 10 centimeters. This is 10, which is exactly the focal length of the concave lens. What is the property? Different rules of lenses. If a ray is directed towards, this is also the focal point, do not forget, of that second lens. Then the ray after the refraction will just become parallel. So that is why it will just become parallel. This will now just become parallel. Do you see that? The ray was directed towards that particular focal point. Oh, now once these rays become parallel and they pass through this lens, what will happen? They will again, they will again meet at the focal point. This is a convex lens. Where will they meet? At a distance of 30 centimeters. At a distance of 30 centimeters. So they will meet at the distance of 30 centimeters right of the third lens. That is option number B. So simple. This kind of question had come. This is a combination of lens question. All right, it's just easy, but I want your comments and your attendance, or else I'll take a class and again nobody will attend, means again I'll feel like I wasted my time. So I would want all of you to attend these classes. Okay, so guys, uh yep, let's basically now break out for a break. Okay, for optical instruments, we'll return after the break. It is a very small topic. Return. We'll take a break of 15 minutes or something. Hello, hello, hello. Am I audible, guys? Just let me know quickly in the chat box. Am I audible? Visible? Do let me know quickly in the chat box. Awesome, awesome, awesome. Great. Cool. So let's continue and let's finish this part. Optical instruments. It's very straightforward. It's a simple topic. It's not that difficult. You get standard questions on this, and when you get these questions, you should be able to directly solve this within a couple of seconds. Okay. So now, when we talk about optical instruments, what is the whole idea about this? I'll tell you. There are two things. One is something called as the least distance of distinct vision. Second thing, which is called as is the magnifying power. Let me explain these two concepts first. See, this is the human eye of a pandu. Okay. If imagine he's seeing a champa over here, beautiful champa. If this pandu is seeing a beautiful champa here, if the champa comes close to pandu, if the champa comes close to pandu, the eyes will automatically adjust its focal length so as to see the person clearly, and the image is formed on the retina. So there are something called as ciliary muscles which expand, contract, and accordingly the focal length of the eye changes because the curvature of the eye changes, and that's how you can see the object clearly even if the person goes far or comes close. Now there is a particular distance till which you can focus, okay, after which you will not be able to focus, and that is basically called as the near point. That is called as the near point. And the farthest distance till which you can focus, that is called as the far point. That is called as the far point. Usually for an, oh, by the way, this is also labeled as D. This is labeled as D. For an average human, for an average person, this D is roughly 25 centimeters. When you are just born, it is very less. And as you grow older and older, this distance keeps increasing. When you are in your teens or early infants, it might be 8, 10, 15, 12 centimeters. Slowly, as your age increases, that 25 might even become 50 or even 100 centimeters. For an average person, this far point is at infinity. That means you can focus on stars, distant mountains, very far away buildings. So hence, whatever is there in between, this is your field of vision. This is your field of clear vision. In this part, any champa stands, the pandu will be able to see it. So if there is a beautiful champa over here, this pandu will be able to see this champa as long as she is between this and infinity. With some defects, this far point can be different. This near point also can be different depending on whether you have myopia or hypermetropia. Okay, this is something which you should clearly know. If this champa comes close, she will look blurred. That is what it means. This is the first concept. Second concept is, see, imagine there is a champa over here, and this is our Pandu's eye. This is our Pandu's eye. When Pandu looks at champa, he will see that champa's head and the champa's toes subtend certain angle on his eye. When champa comes close, imagine now champa has come over here. When champa has basically come over here, then that same champa will subtend a little bit bigger angle as compared to before. So this particular angle theta 2 is definitely more than this particular angle theta 1. So when you are far, you have a smaller angle which is subtended. Smaller angle which is subtended. And as you come close, the angle is more and the vision becomes very clear. Because if you are close, that same object is subtending wider angle, so you can see things clearly. But remember, you can't come closer than 25 centimeters on an average, because then you will go out of the field of the vision. So that means wider the angle subtended, the better it is for me to inspect that particular object. You might be like, yes, sir, the Pandu wants to inspect Champa. Fair enough. So what if I tell you, I can make this angle even more using some instrument. So that is exactly what an optical instrument does. See, Champa can't come closer than 25 centimeters no matter what you do, because this is our Champa. She can't come closer than 25 centimeters because that is the least distance of distinct vision. Correct? That is the least distance of distinct vision. So what we do is we use some kind of an optical instrument. It could do some kind of magic. It could do some kind of magic. It could be a convex lens or a concave lens or a combination of lens. So this is our optical instrument. This is our optical instrument. So without the optical instrument, the Champa subtended an angle, let's say I call it theta naught. Let's say I called it theta naught. This is the angle subtended for the unaided eye. Unaided eye. Unaided means without the optical instrument. Now, because of that lenses combination, etc., I might see a bigger image of Champa. Maybe I see the Champa somewhere over here. Maybe I see the Champa somewhere over here. Who knows? Okay, so this is slightly bigger version of Champa, like this. I see Champa like this, probably. Okay, so now if I join the points, it will be like this. This is that bigger angle. I will call it as theta. This is for the aided eye. This is for the aided. Aid means you have taken help. Whose help have you taken? Optical instrument. So when you divide that theta, which is obviously more than theta naught for the unaided eye, that factor is called as the magnifying power. That is called as the magnifying power. Magnifying power of that optical instrument. Now keep this in mind. This word of caution, guys, again over here. That is, this is not the same power which you studied in lens or mirrors. It is not measured in diopters. It is not measured. It is not measured in diopters. Very, very important. It is not measured in diopters. Not just that, see, it is a completely dimensionless entity. Both are dimensionless, guys. Keep that in mind. So it is a completely dimensionless entity, whereas the focal length had a dimension of length. So 1 by length was the dimension of our power which we used in lens. This is just a simple ratio. It is just a simple ratio. It is a dimensionless quantity. Okay, keep that in mind. So you might have seen on a telescope or on a microscope, they mention 5x zoom, 20x zoom. Means if you take an angle of 1 degree of the object, it will be multiplied 20 times or 30 times or 5 times. So that is the meaning of that magnifying power. 5 times, 6 times, 100 times, 20 times. So that is that ratio. Is that now clear? Are these two concepts clear? The concept of the field of vision from far point to near point, as well as the concept of how the angle makes the image perceived to be very clearer, and you can improve that by taking the help of a optical instrument like combination of lenses or just a simple magnifying glass like you can see over here. Okay, now by the way, guys, I think many of you have forgotten to smash the like button. If this continues, I think next week I will not be taking classes. Hmm. If this continues, I'm warning you guys, I won't be taking classes because I'm doing this for you. I'm standing over here from you. I expect that bit of appreciation in terms of comments, in terms of likes, in terms of shares, in terms of you telling your friends and batchmates, sir is teaching over here. You need to attend the JEE English classes. If we're not going to do that, there is no point. Okay. So smash the like button right away, right now. Let others also know. Now let's talk about simple microscope. It is nothing but a simple convex lens, guys, nothing more. So uh, I'll just show it to you right over here. See, if you take a convex lens, assume that our eye is over here. Let's say this is our object. Okay, that same diagram is just shown over here. Okay, I'm just drawing it. I'm making you understand how it works. Uh, Let me also show the principal axis. Okay. Now, the focal length of this lens is this much. So this is the focal point. And this object is here. I want to see where the image will be formed, especially if you bring the object lesser than the focal point, then the image is virtual, erect, and magnified. That's a standard thing. So we can just draw the ray diagrams. It's not that difficult. So let's see how the rays will look like. Mm, okay, let's just draw the ray diagrams. So one of the ray will probably just go here, and because it is parallel, it has to go through the focal point. If this much is the distance, this much will be the distance somewhere over here. And another ray which passes through the center should go undeviated, basically something like this. Now you need to extend it behind. So when you extend it behind somewhere here, and even this, if you extend it behind somewhere here, it will probably meet over here. So probably this is the location. Yeah, this is the location where your image will be formed. This is where your image will be formed. It is obviously virtual in nature because if you are seeing from here, it is formed here. You have to extend it. That's why it is virtual. It is also erect in nature. Not just that, it is also, enlarged. It is also enlarged. So all these three distinct characteristics is what we are seeing. Also, we can just say that this whole thing is the image distance, and this thing over here is the object distance. That's what we are seeing. Now, this is exactly what we expect of a simple microscope, which is also simply called as a magnifying glass, like I have shown you over here. It's just a magnifying glass. You take a convex lens and you place whatever you want to see lesser than the focal length, you will see a virtual, erect, magnified image, exactly what you are seeing over here. You can see the image is magnified. This is exactly the ray diagram for this. Now, imagine this now. If by chance this image distance is d, if this image distance is d, that means the person will perceive the image to be as close as possible. That can't be lesser than that. So this is your least distance of distinct vision. And under such circumstances, your eyes are strained. Definitely, eyes are definitely strained, but that's okay. I'm ready to take that pain for some time to see it clearly. You will notice that the magnifying power comes out to be 1 plus d by f. This is for least distance of distinct vision. Okay, this is that special case where you will see that the image which is formed is at distance d and the eyes are strained and the magnifying power is 1 plus d by f. That is very important. But second scenario is also very crucial. If the image distance is very, very far, That means it is formed at the far point. When this happens, you also call it as the normal vision. You also call it as the normal vision. Your eyes are relaxed. No strain on the eyes, less strain. Eyes are relaxed because you're focusing on infinity. So you place the object close to the focal point, the image will be found very far, but it will be very magnified. Then the magnifying power is just capital D by the focal length. As simple as that. So these are the two major formulas for a simple microscope, and you should know the conditions also for them, where they are. Where they are. V is D versus V is infinity. So if V is infinity, that means object is at focal point, very close to that. As simple as it. Cool. Shall we solve some questions based on this? Shall we solve some questions based on this, my dear students, my dear lines? Okay, let's do this. Okay. What is this? I think by mistake it came. Okay, here is the question on your screen. An object is seen through a simple microscope of focal length 12. Find the angular magnification produced if the image is formed at the near point of the eye, which is 25 centimeters away from it. Most important thing, at the near point, that means at least distance of distinct vision, and that D value is also given to me. So question is, what is the magnifying power? So the magnifying power is 1 plus D by F. D is 25, focal length is basically 12. So 12 plus 25, guys, that's 37 by 12. 12 goes with 36 three times. So it is approximately 3 times. So the magnifying power is roughly 3. I think why did they screw it up over here? This was 3.08, not 2.08. Right? Yeah. So this will be roughly close to 3. Is that clear? Everyone till this point? But let's say if it was not for near point, if it was for far point, so for normal vision, what would be the difference? For normal vision, what would be the difference? The magnifying power will be just D by F. So it will be 25 by 12. 12 goes with 24 two times. It will be approximately 2 times. So there is a difference. You can see 1 degree will become 2 degree for far away, relaxed position. But when you bring it close to the least distance of distinct vision, it will become 3 times. This is better, but this is less, and you have the additional benefit, your eyes are relaxed. Here you have to take some pain, eyes are little strained, more, but the magnification is much better. Okay, I hope this is absolutely very clear. Moving on to the next question on your screen. Yes. Okay. Oops. Why is the answer there here? My goodness. Sorry, guys. Why is that answer? 1 second. Let me just remove this. Okay, let's solve. A lens of focal length is used to magnify a glass. The near point is 25, okay, and the lens is held close to the eye. The distance of the object from the lens, the angular magnification when the image is formed at infinity. Okay, all the things we have to find. So first things first, let's solve it for the near point, when it is near point. So near points, if the near point wala situation is used, the magnifying power will be 1 plus D by F. D is 25, F is 6.25. So 25 by 6.25 is 4. So therefore, this will be basically 5 times. Whereas if you go for the far point, when the image is formed at infinity, then it will be just D by F. So it will be 25 by 6.25, which will be basically 4 times. So clear-cut distinction is there. But there is another question, where should the object be from the lens? When this happens, when you are talking about normal vision, when you are talking about the normal vision, then it is very, very clear. The object is going to be at the focus. The object is going to be very close to the focus. So the focal point is how much? 6.25. So very close to 6.25 centimeters. Then the image is formed very, very far away. But for this situation, what you will do is just imagine this convex lens. This object is here. The image is over here. This image is at a distance of 25 centimeters. This is your image. I don't know where the object is. So focal point is over here. So using 1 by v minus 1 by u is equal to 1 by f. V is negative 25. Object distance not known. Focal length is basically 6.25. So take 1 by 2 u on the other side. So I'll get minus common 1 by 25 plus 6.25 is actually 25 by 4. That's how I'll look at it. It will be easier for me to solve. So therefore, negative 25 is common. So it will become 5 by 25 is basically 1 by u. 25 goes with 5 times. So u is basically minus 5 centimeters. So if you place the object, so the object is now at 5 centimeters from the lens, then you will see that the image is magnified the most and the magnifying power is 5 times. That is the answer to this. That is the answer to this. Everyone, clear? Shall we go ahead? Amazing. Let's go. Let's go. Okay. That is what the answer is. Now let's go to compound microscope. It's basically two simple microscopes together. It becomes complex or compound microscope, which you have seen in the laboratory. Maybe you have seen some blood vessel or some blood cell or some hair or some amoeba or some bacteria or something. So that is used exactly for that. And basically, it takes the advantage of a simple microscope and magnifies it further by taking help of another lens. So there is a lens which is close to the sample, which is our object. So that is why the lens over here is called as objective. From here, you will see your eyes are here. So the lens on this side is called as the eyepiece. So this is called eyepiece. This is the objective. And the distance from the eyepiece to the objective, that is called as the length of the microscope. You would have seen there are a lot of adjustments on the microscope. You might have to change the length of the tube so that you can focus it properly. Also, you have variety of lens options. So you can turn it around. So if you want to change the power of the lens, it might be written 5x, 10x, 100x, 200x. You can change the focal length by adjusting these lenses one after the other. So you have the options of changing the focal length here or the tube length over here, and so that you can focus it very clearly. What is some interesting thing about the compound microscope? How many of you have seen through a compound microscope? You will see one interesting thing. The image which is formed, obviously it is virtual, obviously it is magnified, but it is inverted in nature. How many of you remember doing this? You move the slide to the right, the image moves to the left. You move the image away from you, it feels like, sorry, the object away from you, it feels like the image is moving towards you. So guys, you might have seen this when you move these slides, the images are actually inverted. Okay, especially in a compound microscope. How many of you have noticed it? If you have not, try it next time. Yep. Samir, this will be much more than NSCGS. I mean, this is for JEE Advanced and JEE Mains, of course. So what is so special about compound microscope's ray diagram? Let's have a look at it. Okay, it's simple, guys. This is your eyepiece. This is your objective. Your bacteria, amoeba, whatever is there will be over here. Objective, that's why this is your object. Sometimes you can call it as O1 also. This first step is basically where you will place the object slightly beyond the focal point, and you will see that there will be an inverted image on the other side. You will see that there will be an inverted image on the other side, which is magnified, something like this. So this is the first intermediate image. This is the first intermediate image which is basically formed. It's formed by the objective. So if I call this object distance 1, this would be image distance from our lens of objective. I can call this UO and this will be basically VO. O stands for objective, U for object, V for image. Object distance, image distance. This image will behave like the object for the next lens. So I can probably say this distance over here is object distance for the eyepiece. That's how it behaves. But it is placed in such a way that this eyepiece behaves like your magnifying glass. Magnifying glass. It behaves exactly like that. And if you remember what is the ray diagram for a magnifying glass, you place the object lesser than the focal length so that you get an erect, virtual and enlarged image. So what happens over here, you will get an erect, enlarged virtual image. So this will make an image somewhere over here. This will make a final image maybe somewhere over here. This is your final image. You can see it is erect. You might be like, sir, no, sir, it is inverted. See, it is inverted for the original object, but for this object, it is actually erect only, if you think about it carefully. So this is our final image which is formed and it is completely inverted, and this is your final image distance. This is your final image distance. For this to happen, obviously, you have to place it before the focal length of the eyepiece, and for this inversion to happen, obviously this object should be beyond the focal length of the objective. I hope this is absolutely very, very clear. Now if I ask you what is the length of the tube, of the microscope, which basically goes from here to here. This is the length of the tube of the microscope. Think about it, my dear warriors. What is that length of the tube of that microscope? Yes, the length of the tube of the microscope will be this distance plus this remaining distance. How much is this? That is basically VO, image distance from the objective, plus this distance, which is object distance from the eyepiece. That is the length of the tube. As simple as that. You can also use lens formula 2 times for each of them. Like you can say 1 by VO minus 1 by UO is equal to 1 by focal length of the objective. You can also use the same thing again here. 1 by VE minus 1 by UE is equal to 1 by FE. So using these lens formulas 2 times, you can find the final image. You can use the lens formula 2 times and you can find the location of the final image, and you can see very clearly what is the nature of the image. The final nature of the image is obviously inverted as compared to the original object. It is 100%, it is inverted. It is also highly enlarged. You can see that is the whole objective of this. Not just that, it is also virtual in nature. So that is the nature of the final image. I have also shown the ray diagram over here for your benefit. In case you wanted to see how the ray diagram is, it goes like this. You show the ray diagram, it forms an inverted image intermediate here, and that image is the object for this lens, and it makes a final image over here. You're like, sir, in this ray diagram, the image is formed beyond the objective. There is no harm in that. It can be anywhere, guys. So don't think it has to be above this or below this, nothing like that. It can be anywhere. So don't get confused, sir, why did you show it here? It's just happening. Okay, it depends on how the focal length and the object positions are. That is how it works. Clear till this point? Right. Now, you might be wondering, sir, what is the formula for the magnifying power? You tell me that first. Okay, fine. I'll tell you the formula for the magnifying power. Now, there are two situations again over here. One is normal vision, one is what do you say? Um, this thing, least distance of distinct vision. Irrespective of that, the formula is the same. Only one small thing changes. I'll tell you what changes. See, in general, in general, the magnifying power of a compound microscope is, be careful over here what I'm writing, magnification of the objective lens of the objective lens multiplied by number 2 is magnifying power. Remember, this is a magnifying glass. Magnifying power of that magnifying glass, which is your eyepiece. This is the formula. That's it. This is the formula. If you remember this formula, you can solve any question. This is the general formula. This is your general formula. Now, what happens is this magnification will be always VO by UO. Normal lens magnification, V by U. That's it. That is that formula. Is that right? Always. Very good. This is where the change happens. And this can be different. Depending on whether it is normal vision or whether it is, what do you say? Whether it is normal vision or whether it is least distance of distinct vision. For least distance of distinct vision, this is 1 plus d by f, which is exactly the same formula for magnifying glass, just that the focal length we are referring to is for eyepiece. So I'll just put eyepiece here. If we are talking about normal vision, when it is very, very far away, so for normal vision, the only difference will be this will be just d by fe. That's it. That's the only difference. That's the only difference, guys. That's all. Got it? Everyone? Now, is it absolutely very clear? Blur. Why is it blur? It should be fine only. Yeah. Just check your resolution and internet speed. Now, in some microscopes, what they do, in some special cases, they usually, forget this part for now. Usually, what they do, that is very, very important. Usually, the object is placed, close to the focal point of objective. And when you do that, what happens? When you place it close, the image is formed very far away. Then the image is formed far away, close to the eyepiece, close to basically the eyepiece. And when this happens, this particular assumption, then you will see our image distance. Where is the image distance going to be? It will be the length of the tube. Approximately, it will be the length of the tube. And the object distance will be the focal length of the objective. It will be L by FO. That's why in some places you might have seen this formula as well, where they have used L by FO, and you might have wondered where did this come from. It is because of this particular assumption. Usually that might happen. That might be the case, a special case. So if the object is placed very close to the focus, the image is formed very far away. And where is it far away? It is here, somewhere close to the eyepiece. So the length of the tube becomes the image distance. As simple as that. With this piece of information and this piece of information, I think it's a good time that we start with some questions. Okay. Say for example, they tell you the focal length of the objective is, let's say, 4 centimeters. Focal length of the eyepiece is, let's say, 50 centimeters. Okay, and we are using that special case scenario where the length of the tube is given to be, let's say, I don't know, maybe uh, 80 centimeters or something. Okay, and the question is, find the magnifying power of that compound microscope. Magnifying power of the compound microscope. That is the question. When you see the focal length of the object is very small as compared to the focal length of the eyepiece or the length of the tube, then these approximations do work. Then whatever these approximations I have written over here, they will work. So you can see it is very much valid. Focal length is very small as compared to these two things. So we just saw what is the magnifying power. The magnifying power is basically the magnification of the objective multiplied by the magnifying power of our eyepiece. Now, guys, over here, the magnification of the objective, what will that be? It will be L by FO. It is V by U. V by U is basically L by F. That point is clear. Why is that case? Because the tube is very large. Focal length of the eyepiece is okay large as compared to the objective. Objective is very, very powerful. Okay, that much point is clear. Now, this part, usually remember, whenever you use the microscope, how will you use it? Will you use it in normal vision or will you use it in LDDV? Why will you be watching it normally, guys? You will be putting a lot of strain because you're trying to study it. So that strain is justified. So you will strain your eyes and watch it at least distance of distinct vision. So that is something which is self-understood. So it will be 1 plus D by FE. So my dear warriors, this will be then length of the tube 80, focal length of the objective 4, 1 plus D by FE. D is basically 25. Focal length of the eyepiece is basically 50. So what will this become? 80 by 4, guys, that is 20, multiplied by this goes with this 2 times 1 plus half is basically 3 by 2. 2 and 2 goes 10 into 3, that is basically 30 times. So the magnification is 30x. 38 times of magnification. That's crazy. That's a good magnification. Kavinram VS, yes, I was born from Tamil. I was born in Tamil Nadu in Salem. Yep. Okay. What a brilliant, brilliant question, guys. Okay. Let's see one more question over here. Let's see one more question over here. Read the question. This time, I feel we might not be able to use our yes, approximations, because you can see the length of the tube, no, length of the eyepiece, focal length of the object is 1 centimeter, eyepiece is 2.5, they are comparable. Okay, and object distance is given, guys, 1.2. So it is not exactly at the focal point, so the approximations may not work. These approximations, whatever I have shown you, will not work, because these approximations only work when you place the object near the focal point and the tube length is large and all those things, which is not the case over here. So now we have to go via pure solving. And when I say pure solving, that means I might have to use the lens formula 2 times and then solve it properly. And then I might have to use the general formula which I have given over here. Okay, so let's do it. No issues. Let's find out. First of all, we have our objective lens. Object is placed at a distance of 1.2. This is the distance of 1.2 centimeters. The focal length of this is 1 centimeter. This is our object. So using 1 by VO minus 1 by UO is equal to 1 by FO is FO. I will get 1 by VO minus 1 by UO. UO is basically 1.2 but with a negative sign, is 1 by FO, which is 1. Therefore 1 by VO, first of all, let me just create a duplicate. I'm going to need a lot of space. Okay, this will go on the other side. So it will become 1 minus, because minus minus is plus, on the other side will become minus 1 by 1.2, which is 1 minus 1.2. I can just write it as 12 by 10, right? 12 by 10, which is 6 by 5, right? Which is basically 6 by 5. 1 minus basically 5 by 6 is basically 1 by 6. So therefore, VO is basically 6 centimeters. Image is formed at a distance of 6 centimeters somewhere here. So this is where the image is formed at a distance of 6 centimeters. Till this point, are you clear? Let me know, guys, quickly. Can we put it as 1.2? Yes, you have to put the object distance as 1.2, nothing else. Okay. Everyone? Very good. Now, that is not the story's end. Okay. That is not the story's end. We have to do something more. It is clearly mentioned. Find the angular magnification and find the length of the microscope's tube. Everything is mentioned. So for the tube's length, what else will I need? For the length of the tube, I will also need the image distance. Oh, the image distance I know. Okay, this is now straightforward. Okay, got it. See, guys, this is our objective lens. Okay, this is our objective lens. Our eyepiece is somewhere here. Our eyepiece is somewhere here. Our first image was formed here at a distance of 6 centimeters. At a distance of 6 centimeters. Okay. 1 second. Yeah. I need just this much distance, which is the object distance from the eyepiece. If I know that, I can immediately find the length of the tube. I can immediately find the length of the tube. Correct? So how do I find the object distance for the eyepiece? It is clearly mentioned that we are using it for the normal adjustment. If we are using it for the normal adjustment, think about it. Yes, the image will be formed very, very far away, very close to infinity. That means, for normal adjustment, think about it carefully. Think about it carefully, guys, for normal adjustment, because the image will be very, very far. That means this distance, UE, how much should it be? It should be almost the focal length of the eyepiece. The focal length of the eyepiece is given to be 2.5. It is just given to be 2.5 centimeters. Do you see that, my dear students? Everybody with me? It is clearly given to be 2.5 centimeters exactly. So hence, I can clearly see that the length of the tube will be the 6 plus 2.5. Therefore, the length will be 8.5 centimeters long. So that is one of the answers which we wanted. Find the length of the tube. Last is find the angular magnification. So for that, because we are using normal vision, it becomes very simple. The magnifying power will be this V by U, this image distance by object distance, V by U, multiplied by the magnifying power for your normal vision. Which is having the formula D by F. D by F. Okay, fair enough. What is D? 25. What is the focal length? That is 2.5 for the eyepiece. Next, what is V? Image distance, which came out to be 6. What is object distance? Object distance was 1.2, I believe. Perfect. This goes with this almost like 10 times. 6 goes with 12 2 times, but this is decimal, so this is 0.2. So guys, this will be nothing but 100 by 2, which is 50. So just check it out. The magnifying power will be 50 times. That is the other answer which we wanted, angular magnification, which is 50 times. Got it, my dear students? Yep. Everyone, how to find this out? So this was a general formula, V by U, which is the magnification of the objective into magnifying power of the eyepiece. So I just used that and I got it. Exactly. Ray optics are starting chapters, Chaputa sir. Yes, starting chapters. Starting chapters are here. You go down. Where is it? Oops. You can go to home page also, my dear students. You can go to home page. Yeah. JEE mains and advanced past live streams. Okay. See this complete physics. Complete physics. Go to the playlist. Can you see? Units, dimensions, vectors, motion in 1D, motion in 2D, ray optics, electric field, Gauss law, ray optics, okay, relative motion. All the chapters will be put over here only. Okay, I've done the starting chapters. Don't worry, all the capacitance will come, then current electricity will come. All those chapters will be put up here. Okay, great. Cool. So that was that. Let's go to the last one, which is astronomical telescope, which we have again in the syllabus. And the main difference between a microscope and a telescope, actually there are many, is that in case of a microscope, you place the object very close to the lens, like you're watching some tissue and it is very close. But for a telescope, the object is very far. You are seeing a star, sun, moon, planet, Jupiter, this, that. So it is very far. Number one, that's the main difference, guys. Number two is that the type of the lenses that you use on objective and the eyepiece is also different. There is some effect called as diffraction which happens, and because of the diffraction effects, you have to ensure that the images are resolved in case of a telescope. So when the light comes from very far away places, and if you have a small hole, that light might get diffracted and you might see some double images, triple images, which might make it blurred or not so clear. So there are diffraction effects which need to be taken care of. Third thing is that the amount of light that you get. Say when you are watching a tissue or a cell or a hair or some small object under a microscope, you illuminate it from below. There is light which comes from below, and that's how you are able to see it very clearly. But when you are seeing Jupiter, no god or no person is standing with a torchlight there. Hey, let's see Jupiter. So the light that comes inside our telescope is very, very less. So in order to see it clearly, you need to ensure that the objective lens, this is the objective lens because it is near the object, that has to be really huge so that it can collect as much light as possible. So these are the three major things which you should keep in mind for a telescope. How does the ray diagram look like? It is drawn over here, in fact, but I will just show it to you. This is eyepiece, this is objective. Your object is obviously going to be really, really far, guys. So I can't even show it over here. That's something which you should probably really understand this, but still I'll just show it a very different way. This is infinite distance, and infinite is just a way of saying it is really, really far. So our object is really, really far. The rays from it come and they are collected at the very close point to the focus, because when object is far, the image is formed intermediate. This is your intermediate image. which is formed very close to the focal point of the objective lens, FO. This image now acts like an actually FO here. This image now acts like an object for the eyepiece, and please mind it again, just like before, the eyepiece acts like a magnifying glass, exactly like before. So remember, for a magnifying glass, if you place the object at a distance lesser than the focal length, then an erect, enlarged, and virtual image is formed. So ensure that for the next lens, the focal point is somewhere here, or probably somewhere here, something like this. This is your FE, and because of that, what happens, you will see a very, very nice big image formed very, very far again, because it is very close to the focal point. So this is your image which is formed. It is virtual. You can see why it is virtual, because your eye is there, you have to see it from the other side, only then you see the image. It is also inverted as compared to the original object. Not just that, it is also enlarged, which is the main purpose. You have to enlarge it, so it is enlarged. Again, you will also see one more thing interesting. This distance, which is, once again, this distance of the image, which will now be the object, will be the object distance for the eyepiece. And this distance will be the image distance for the objective. So when we refer to the length of the tube, this particular length of the tube is nothing but your image distance from the objective plus the object distance from the eyepiece. This distance plus this distance is the length of the tube, something which is again very, very visual, very, very obvious. Is that part clear till here? Excellent, eh? Awesome, great. Lastly, the image magnifying power. This is very important. The magnifying power of a telescope. See guys, you might be like, sir, are there now two things like normal vision and distinct vision? No. You always see the object under the telescope in such a way that the image is formed really far away. This image is really, really far. It's okay. I don't want the Jupiter to be seen in front of my eyes. It's far, and you watch it in a relaxed manner. So it is always in normal vision. Keep that in mind. So this is in normal vision, and that comes out as FO by FE. That's it. So that is the formula for the magnifying power, FO by FE. Okay, so that will give you how many times the image gets magnified. As simple as that. Okay, it's exactly the same thing which I have shown in the ray diagram over here. The rays are coming from very far, making the image here intermediate. This image acts like the object and makes a virtual enlarged image on this side. Exactly what I have shown over here. Okay, cool. So now let us see the questions on this. Let us just see the questions on this. If you see the questions, you will be like, yes, sir, this is so simple. I mean, actually, it is simple. Microscope compound one is the only tricky part. Simple microscope is also simple. Telescope is also simple. Only the compound microscope. I've shown you both the problems. That's it. Okay. Cool. Erin Jagger, Champa love story, sir. Champa is now very, 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 very serious about studies. Champa is like, no, sir, I have to study, sir. JEE means 5 months gaundi, sir. JEE means 5 months away, sir. We have to study. So Champa is sitting with, uh, yeah, Champa is sitting with Pandu, with him in this lecture. Sorry. Astronomical telescope has an objective of focal length 200. eyepiece of focal length 4. The telescope is focused to see 10 kilometers. 10 kilometers is very far away. The image is formed at infinity, that is very far. Find the length of the tube and the angular magnification. Length of the tube, I just told you, it is FO plus FE. So it is basically focal length of the objective plus focal length of the eyepiece, which is 4. So it is just 204 centimeters. Perfect. That is the first answer. The second answer, the magnifying power, FO by FE. That's it. Bigger number here is 200, smaller number is 4, guys. That's 50 times. So the magnifying power is 50 times. That's the answer. So either you will be given this, or you'll be given this, or you'll be given this, and you will be asked to find the other two. That kind of questions do come in the JEE exam. That's all. Very, very simple, simple ga undi. Yes. Okay. So it is 50. Perfect. And that is the end of ray optics. So guys, if you notice this particular session, I don't know, what is it? Almost like 10 o'clock. We started at 5 o'clock, right? So we have taken good 5 hours for this class. The previous lecture was also a long class. So we have given a good amount of time for ray optics, but obviously we'll need to practice more questions, and we'll do that in the problem solving series. Cool? So guys, I need one favor, one help from you. All the people from Telangana, all the people from Andhra Pradesh, all the people from Tamil Nadu, all the people from Karnataka, all the people from Kerala, all the people from Maharashtra, all the people, who are studying in many of the other countries abroad, like UAE, right? Or even some students are studying from Nepal or Sri Lanka, and some students even in many of the northeastern states. I was just seeing Nagaland, Mizoram, right? So many places. People love to learn in English. Let your fellow mates know about this channel. Let your friends know about this channel and attend in full strength, because you are getting quality content, guys. Yep. And that too detailed classes. So you should not hesitate to comment, to like, to share, to talk about Captain Shreyas Sir, to talk about this particular channel. Yep. Okay. So also remember one thing. As you are watching this video, I have also pinned a message, probably, hopefully, maybe not here. Okay. In this, there is also a JEE English batch for the 12th standard dropper students. Okay. You can join that JEE English batch where you get complete syllabus coverage, 11th, 12th, along with revision, test series, along with your assignments, hard copy of the material, ebooks, doubt solving in the class and outside the class, as well as you get your personal mentors and the best teachers in the country. Fill this form, talk to the counselor, and then decide. I am not saying join the batch right now. I'm just saying just inquire if you are looking forward for a serious preparation. If you're not serious, then it's okay. If you are serious, only then fill this form. You can fill this form, and you have multiple options. Online, offline is also there. If you are especially near one Vedantu learning center, which is our offline learning centers, and you want to study properly offline, that is also there. Online batches are called pro batches. So this is the form for your pro batches. If you're 11th standard student also, you can fill it. That option is also there. If you notice, 11th, 12th dropper, all the batches online, offline are available. Fill this form. Okay. I hope this is clear. Okay. Okay. Deepak Mithrian, no bacha, it is not good. It's gone down the drain now. It's no longer good. There was a time when it was good, but now it is just running based on past glory and all that. Now they are not paying their salaries, they are not giving additional material properly. It's no longer the same old institution. So I wouldn't consider joining that. Okay, cool. Thank you guys. Have a great time. See you. Bye bye. Hasta la vista, Captain Shreyas signing off. Take care. See you in the comments and smash the like button.